Just start? We're going? Okay. All right, so the few, the proud today in the classroom. Nice. So this is scheduled to be lab exercises. So for the first part, we're just going to try and go through and solve a few problems. Just get some practice with some of the things that we've talked about. And we're going to start off with D-spacing measurements. And there's a lot of ways, we could go to TEM spot patterns and these kind of things, but we're going to focus on X-ray diffraction that we looked at, or that we discussed, and then compare that with what we get from EBSD patterns, okay? So here's the problem. It says I'm giving you X-ray spectra. So I'll show you those in a minute. One uses silver anode and one using copper anode as the X-ray source. And it says make sure the crystal structures look correct, identify the D spacings of the first three peaks. Are these consistent with each other and with aluminum? And what kind of uncertainty do we think we get? Okay, so here's the, did you give them, Somji, did you give them all of the files in that SPARC course? Yes. So you have access to the Excel files, you have access to all of this that I'm showing you, okay? Okay, so the first one, this is just what you have in your file. It's just these two columns of data, just the 2 theta value and the intensity. And so we're going to come and we say, we were given in the problem that this is FCC, right? We were told it was aluminum, so we know it's FCC. So, can I write on this? I think I need, okay. So we know it's FCC, so what kind of diffraction peaks do we expect from FCC? Do you remember the selection rules that we talked about? All odd or all even, right? So here we have FCC. So if we start scribbling out what the possible HKLs are, we can start with 100, right? I try and do this in the order of h squared. Oops, I'm going off my sheet. It doesn't let me do it when I go off. H squared plus k squared plus L squared, right? So that's 1. So 2. If I have 111, that would be 3, right? If I go to 200, that would be 4. 210 would be 5, right? We have a 211 for 6. We have a 220 for 8, right? And then we have a 221 or a 300, which would both be 9. I don't know if I skipped any. Okay, all odd or all even is the selection rules. Okay, so 100 doesn't work. 110 doesn't work. 111 does work, right? 200, that one works. 210 doesn't work. 211 doesn't work. 220 works. This one doesn't work. This one doesn't work. Right, so the first 3 peaks we would expect, 110, 111, 200, 220. So we expect that to be 111. We expect this to be 200. And we expect this one to be 220, assuming all the peaks are available in the spectrum. Okay. All right, so if I look at these data over here on the left side, I know I'm somewhere around 44 degrees, something like this. And so if I look at the actual values here, and this is straight from a X-ray system, right? This is just an Excel file, a CSV file that I exported from come on, can I scroll? I can't scroll. So I'm looking at the intensities in column B, And I see at 44.8, it's 19,000, so it's getting high. 25,000, 30,000, 29,000, then it goes back down. So my peak is right here at about 44.89 to 44.9, right? So let's say this is, remember what value is this in the column on the left? Do you remember what value? 2 theta, right? So we have to divide by 2. So let's say theta equals 22.45, something like that. Okay. All right, now in our problem statement, it says that the cobalt anode that we've used is 0.179 wavelength, 0.179 nanometers. So then it's easy to come in here and we have in lambda 2d sine theta, right? And we're going to just set to 1. So then we have lambda equal 2d sine theta. We're looking for the d spacing. All right, so real simple. So we know this value, 0.179, that's nanometers. What do we say, 22.45, is that what we said? So what value do we get? Somebody have a calculator? And the other one we need to do is we need to compare that with what we know is real. So we have, for cubics, so what values? Did somebody calculate a value?
2.3 angstroms.
2.3?
Angstroms.
Okay. 0.23 nanometers I'm going to put since I had that in nanometers. Okay. 0.23. Now we know the equation for d-spacing for different symmetries. Now aluminum has a lattice constant of 4.05 angstroms or 0.405, something like that, right? Does that sound right for aluminum? Okay. So we have that squared, square root, so we have 0.405 divided by the square root of what HKL did we say that was? First peak, 111, right? So we have to divide that by a square root of 3. So what value do you have for that? I'm hoping it's 0.23. Somebody do the math quick. What did you get? 3.9. That doesn't seem right. 0.405 divided by the square root of 3. Throw that calculator away, try another one. 0.23? Okay. So that means it's consistent. What we got from the measurement was consistent. Now what do you think the certainty in the measurement is? How would we determine that? We've got to go back here. All right, here's the two we were looking at, right? So we said it's somewhere between 44.89, 44.90. And then we estimated it at 22.45 and we got the right answer. So what if we called it 22.445, right? That would be this value divided by 2.
From the angle we are calculating D. From the
Calculating D.
D.
Mhm.
Okay. So
From the X-ray data. Yes.
this is the peak. At the angle at which we get the peak. There.
Right. So this is the peak that we're looking at.
Okay.
And the way we got that is we had, well, let's say 22.4. 22.45 would be about here, 22.445, right? 2 4s and a 5. 22.445. I was just going to say, remember that, 22.445. So we got that from, plotting this X-ray data and saying that's going to be a 111 peak, and we know it's about 44, so then we looked at the actual data to determine exactly where the peak was. Okay? So let's do this with 22.445. So do this calculation again, but instead of 22.45, use 22.445. Whoever did that math, let's plug that one in. One, 2, 3, 4, 4. And the other one was 0.23, close to that, right? So the uncertainty is going to be somewhere in these third, fourth, fifth digits, right? So we can get it to within a fraction of a percent, probably, right? It's probably a part in 1,000 or a part in 10,000 that we can measure it at. Right, we get the nice sharp peak where it is. Okay. All right, so that's what we do for X-rays to measure D-spacing. Now we're saying, okay, we have an aluminum pattern, and we're going to estimate the D-spacing. That's going to take a little bit more work. So you're going to have to help me out here. I've opened ImageJ. I don't know if you guys use ImageJ. It's a free download, right? So I pulled open ImageJ, I pulled open the aluminum pattern. This is a 480 by 480 pattern. I do have another pattern that's bigger, so I have a 1024 by 1024 pattern. Right, we could get a little bit better resolution if we showed all the pixels instead of bending it down a little bit. But the aluminum pattern I had was 480 by 480. So we're going to play with that. I've marked the position of the pattern center on there with this white dot. So what do we need to know if we're going to measure bandwidth? Oops. If we're going to measure D-spacing. Kind of I gave you the answer, right? You need to go to the bandwidth angle. And remember that, let's click back to this one. Remember that the geometry of the diffraction is such that if you have your specimen, you have your electron beam here, you get a diffracting cone that comes like this off the top, you get a diffracting cone that comes like this off the bottom. All right, so this is the bandwidth angle. We said that was 2 theta. All right, so the bandwidth angle we're measuring is 2 theta. All right. So what do we need to know? How do we do it? I'm going to do a measurement. This is usually how I do a measurement. Just draw a little line segment. What line segments do I draw? We need to know some stuff first, right? So what's the first thing we did with the X-ray patterns? Do you remember? We said, what peak is this, right? We saw the peaks, we said, okay, which peak is this? So it would be nice to know what the crystallography of these things is. Now you guys haven't had the experience that I've had in looking at all these patterns, but if you're just looking at this and you know it's cubic crystal symmetry, do you see some symmetry anywhere in there? You see mirror planes, you see two-fold, three-fold, four-fold axes. Where do you want me to go to? Up at this peak? Which would zone axis? This one? Okay. So what kind of zone axis is this, do you think? I heard somebody start to say 3, but they stopped. It was like a 3. Okay. If this is a threefold axis, this has to be the same as this, has to be the same as this, which means that must be a mirror plane, and this must be a mirror plane, and this must be a mirror plane. Does it seem right? Is this a mirror plane? We look at these peaks, yeah, they could be right. These could be the same. You can't go further out, right, because we lose the data up here. This is a busy zone axis. It looks like there's a busy one out here, so I could believe it's a threefold. So this would be our 111. Right, that peak right there is our 111. So I can come back here to the pattern and say, okay, that's a 111 zone axis. And I'm going to draw this. I was going to draw it with pointy braces, but I'm going to draw it with square braces. Because we'll say it's a specific 111. Okay, so we know that. And then just knowing diffraction from how FCC patterns work, this is going to be a 211 type. Now, should I call that a 211 or a 121 or a 2-bar 11? What should I call it? The only thing is it has to be consistent with what I've defined as the first one. So I call the first one 111, everything positive. So I'm going to need everything positive. And I can call it 211 or 121 or 112. It really doesn't matter what I call it. It's just the others have to be consistent with that, what I've called it. Okay? So now if we're going to work on this band, let's say we're going to try and find the bandwidth angle of this band. What band is that? How do we determine that? What does a zone axis mean? We've said these are zone axes, these directions. Say that again. Intercept of multiple planes, right? So both of these lines lie within this same plane. So there are two lines in a plane. So how do we determine the normal to that plane? Cross product. Okay, somebody do the cross product. 211 with 111. You guys are good getting papers out. My students in US usually have their laptops and they bring up some kind of app and say, they don't do anything by hand. Slackers. It's okay. Say again.
0, 1 bar 1.
Like that? Does everybody agree with that? Okay. So it's a 110 type. Now we're talking about FCC crystal structure. Right? Do we get any diffraction from 110 family? No, right? So what does it have to be then? We do get diffraction from 220, right? So it has to be a 220, right? Because they're parallel to each other. So 220 is the plane that we're going to use for diffraction comparison. Okay. Back to here. Okay. So we're going to cross out 011. We're going to use 02. Okay. Now, once we calculate that, we have to make sure that the dot product with our different zone axis is 0, right? They have to be normal to each other. So 022, 02, bar 2 has to be normal with 211 and 111. And it is, so that's good. And this little zone axis down here, right there, that's going to be a 233 type, just because I know what the diffraction does, right? And then we have another 011 down here is going to be an 011. Okay, but all of that doesn't matter. So we know that is 02 2 bar. Okay, so let's go back here. Have our pattern. Now we have to measure, remember when we measure it, we have to measure in a line that's normal to that band that intersects this pattern center. So we have to measure approximately this length from here to here, one side to the other, right, of that band. So I measured the length. It told me it's 22 point something up here in my bar, but that doesn't help me too much, right? I need to know what the angle is going to be. So to do that, we're going to measure all the way from the pattern center out to the other side of the band. And what do I have there? Length is, can you read that up there? It's 85.51. Okay, so length from my pattern center to the back side. I've got 85.51, and that's just in pixels. And let's measure to the near side. Whoops. And measure along the same line, approximately. Measuring to the near side, I'm getting 63.79. Okay. So this effectively is telling me, I was going to draw on here what it's telling me, but I've drawn this so it's almost normal. Let's say, so this is the phosphor, the way I've drawn this. This is the specimen. And remember, a line normal to the phosphor that intersects this position is the pattern center. Right, that's the line of the pattern center. Now the way I've drawn this 2 theta is in the way here of that, so this approximately is exactly along this line. But I'm going to cheat and say, let's pretend like it's right there, that's the normal. Okay? So I've cheated. Is that going to throw you off? Do I need to redraw it? Let me redraw it. I'll redraw this quick. Same image. That's the bandwidth angle. 2 theta. This is the line normal to the screen, which gives me the pattern center. Okay.
Now, how do you know pattern center is there?
We calibrate it.
Calibration.
Yeah.
Okay.
Yeah, we calibrate it in there. Okay, so we have the pattern center. Now on this image I showed where the pattern center was. Right, on this one we've been playing with, the pattern center is this white dot here. On this one, we just know it's up in that range somewhere, just above this. So specimen to screen distance, we're not exactly on a zone axis. And so the way we do this is we go to known zone axes from that position and we triangulate, just like a GPS calculation to say where you are. Today we're not going to do that, we're going to cheat. Is that okay? We're going to cheat. We're going to say, let's pretend like this 233 zone axis is the pattern center, and then we can draw a line from this position or that position, and we know the angle between those bands, so we're just going to determine what the angle, what the specimen to screen distance is, which is what we need to know. So we're going to take from this zone axis to this zone axis and say that's really kind of like going from here out to a little bit past. We're going to say what that angle is, and that will give us our specimen to screen distance.
So which one you are considering pattern center?
This white dot.
This, okay.
Yeah.
Okay, that's the draw.
So if it falls exactly on a zone axis, it's really easy to go calculate.
Yeah.
So we're measuring from the real pattern center, but we're going to do the specimen to screen distance, we're assuming it's actually on the zone axis.
So, and it's perpendicular.
And that position would be perpendicular, exactly, right. So this is perpendicular to the phosphor screen. We're going to shift that position over a little bit. We're going to measure up there, and it tells us that the length is 163.53. Is that what I got? Can you see where I'm looking? I'm coming just right about here when I draw a line. If you're doing that in image J. That time I got 164, and I shifted accidentally with my Parkinson's, and it says 163. So I'm going to call it 164, okay? All right, 164. Now, knowing those zone axes is necessary, so this is a 110 type. That's a 110 type. This one here is a 332. So what's the angle between those two? How do we get it? Angle between two vectors. Just the dot product, right? So that angle is going to give us our specimen to screen distance, because if we say here's, let's draw it on the other side. We measured this distance, which I mentioned, but I didn't write it down, so I'm going to have to go measure it again. So we measured this distance. We're saying this is a specific zone axis. This is another specific zone axis. And if they're known zone axes, we know the angle between them. So if you know that angle and you know this length, then you can calculate that length, which is what we need to do the math for this problem. Okay. So let's come back here. Does everybody understand what's going on, what we're doing here? Any questions? Just going to measure this again, this line segment, coming from approximately where that zone axis is to this zone axis. And it says 165 that time. I think we were at 164 last time, but we're going to call it 165 since that's what I measured this time. We're measuring in pixels. Angle between 111 and 332. Does anybody have it yet? Got to divide by the magnitude, right? Okay, I see a couple people with calculators, that's good. So this is just a step that is calibration. So we're determining the specimen to screen distance in units of pixels that we're measuring in. Okay. I'm waiting for dot product. I could help a little bit. I know the dot product is going to be 8 divided by the
110.
magnitude of, say again?
It is 110, not 111.
Ah, so that's nay. Thank you. Everybody catch that? That was to make sure you guys were paying attention. You guys do that, right? You make mistakes on purpose?
Even if we do without purpose, we say.
Make mistakes on purpose. When I first became a professor, one of the senior professors told me, algebra is best done in the privacy of your own office, not in front of the students. But I always did algebra on the board and I always make mistakes. It's okay. Okay. 3 squared plus 992 and 4 is 22 squared. Six over 9 times 22 squared square root is the magnitude. If I did that right. Oh, this is 2, sorry, because it's 110. 4 times 22 times 22 magnitude. The angle is 110 to 332. 6, right? And then we have to divide by the magnitude and take the acos of that. Magnitude is h squared plus k squared plus l squared square root, right? Do that twice. Somebody can Google dot product and type in the numbers. Say again?
25 degrees.
25? Okay. I'll take it. 25 degrees. Okay. So this will give us what the specimen to screen distance is. So we have 165 here. We know this angle is 25. So how do we get this length, specimen to screen? 10? Oh, tangent. Yeah, you do the tangent. So this angle, tangent of 25 degrees, is going to be 165 divided by the specimen to screen distance, right? Opposite over adjacent. Specimen to screen we call Z star. So what do we got for Z star? Just 165 divided by tangent of 25. $353. All right. So why do we need to know that? Because we had these two values that are showing this angle. Right? So we've measured this value at 63.79, that distance. And that is really stretching what we actually know, right? We only know within a couple of pixels, but let's say that's 63.8. So what's this angle? 63.8 divided by 353. So this first angle, it comes from here. I'm going to scribble it down here. I'm going to call this alpha 1. Opposite over adjacent. And somebody can be doing alpha 2 at the same time, which we measured at 85.5. That's up to this position, right? So this is the 63. And then from here up to this one was 85. So the two angles, and then we're going to get that 2 theta value, we're going to take alpha 2 minus alpha 1, right? So that's the way we get that 2 theta value. I'm waiting for calculator people again. We don't carry calculators anymore, but they're on our phones, right? So most of us have them.
Minus 10 degrees. Other is 13.5 degrees.
Which one are you saying? Alpha 1? Or are you saying this value? 63.8 divided by 353, the A10 of that. 10. Okay. Wow, you're right. I thought you said 10 when you were saying 10. 10. It's good. Just kidding. Okay, the next one? 13.3? 5. Okay. 13.5 degrees. Okay, so 2 theta is going to be 3.5 degrees. Now, what was 2 theta when we did the X-ray measurement? About 45, right? Somewhere around 45 degrees. So this one's 3.5 degrees that we're measuring for the angle, the bandwidth angle. Now that equals 2 theta, so theta equals half of that, right? So let's steal some more space here. Okay, so what else do we need to know? We have Bragg's equation. We're trying to measure D. We know theta now because we've measured it from the pattern. So this is what we lack. So we're at 20 keV. And it's like 0.0045, but I have to look it up. I don't know if anybody has access to that right there, but I have it on one of my slides, so. .0086. And that was in nanometers, not angstroms. Okay, so if we measure the d-spacing then, if we calculate the d-spacing, we're going to have lambda over 2 sine 1.75 degrees, and lambda is 0.0086. One more calculation from you guys. And then we'll just play with patterns for a minute. And I'm scribbling all over. We're finally to the answer though. .14? Okay. Is that correct?
Yes, sir.
Is that the actual correct value for the d-spacing of a 220 band? How do we determine that? Remember what we did up here? So now we have a 220 band. So we have D of 220 equals A, which is 0.405, divided by the square root of 2 squared plus 2 squared plus 0. 0.405 divided by square root of 8. 0.14. Say that again. This is known from the lattice parameter, this one, 0.14. And then the one we measured, we came up with exactly the same, right? Surprises me. It surprises me.
If the calibration is wrong, then it becomes different and then we can correct it.
Calibration's wrong, it comes different. And measuring this bandwidth angle, we can only do to within about 20%, 10 to 20%. Because I'm trying to click on exactly 2 pixels, right? And there's the number of pixels between there was only 20, it was 85 to 63. So if I click 1 pixel wrong, then that's 5% wrong, right? That's 1 out of 20 uncertainty that I have in determining that angle. So the question at the end says, what's the uncertainty in the measurement? And I was expecting we would be wrong and we would say, well, if we shifted it this way, then we'd be right. But it turned out we were right. Turns out I'm really calibrated well with my mouse clicks on the bands, okay? Okay, questions of how to do that. We did it with X-ray, we did it with EBSD. Do you understand the philosophy of why that's 2 theta? A diffraction off the top of the plane, off the bottom of the plane, 2 theta. And then what we've playing with down here with these screwy drawings that I was doing, that's just a 2-dimensional view of what the geometry is, right? So we can see the tangent of the angle. That pattern center gives us a nice reference to take everything from. So even though we cheated on the pattern center calibration, we didn't cheat too much. It was actually pretty close, so we did a pretty good job there. But we got the right answer. Good for us, wow. I'm impressed. All right. Anybody with questions about that before we move on? Okay. That means I explained things really good. That's what that means. Okay, the next one then, EBSD images shown on the following page indicate mirror planes, a 3-fold, a 4-fold, and a 5-fold axis. Does anything have a 5-fold axis? No. Not really. I like that one though. Okay, this is the pattern we were just looking at with aluminum, right? So somebody indicate where a mirror plane might be. We've already discussed, but there were fewer people in the room when we did that.
So one question is that how you determine the pattern center? how you got it?
So question is, how do you determine a pattern center? So if we were to look at this pattern, silicon calibration sample, right? This is the cheating one where we know 110 up here is normal to the surface of the specimen, and we know 20 degrees away is 114, which is right there, right? So that one, if we have a piece of silicon that we line up with the 110 plane, which is right here, with the 110 cleavage plane lined up vertically, we put that specimen in, we'll have a 114 exactly at the position of the pattern center because it's 20 degrees away and we're tilted 70 degrees. Okay? So if we're tilted 70, and it's actually 19.4 degrees, so we have to be tilted 70.6 degrees to be exact. But our pattern center would be right at that zone axis. Now, if we do any other pattern, then we have to determine what that exact projection is where all the angles are going to be projecting around it. A simple way to do it is looking at these bands and seeing where the bands are most narrow. Right, so you look here, it's a little wider here, it's a little wider here. It's most narrow maybe in here somewhere. And I'm going to draw a normal to that band. I don't know where it is exactly, somewhere in here. Draw a normal to that band through there. So that's supposed to be normal to this Kikuchi band, right? Now let's look at this one. Find out where the most narrow position is, maybe here-ish. Something like that. We draw a normal to this one. We can do the same with any other bands, and wherever they intersect should be where the pattern center is. Okay? So just looking at a pattern, if you know nothing about where the pattern center is, you can kind of estimate where it's going to be. Right? We can take any of these and pretty much estimate where the pattern center is if you can see the curvature in the bands and where they get wider and more narrow. That's just the geometry of how the projection goes, right? It's projecting out from the pattern center.
So we need to look for the narrowest part, and
Right.
make it normal, and then another narrowest part, and make it normal, and maybe another, maybe it should be
Right.
no sense.
Right, exactly. Exactly. So geometrically, that's one of the ways you do it. I mean, like I said, we triangulate with when the software calculates it from a random pattern. We know how to index it, so it has to be indexed properly first. And then you're looking where all the patterns are, and you know how the gnomic projection works, so you know what the distortion should be. So you can pinpoint all those and say, okay, that's where the pattern center has to be. So it's just geometry calculations to do that.
It can't be outside.
It can be, absolutely, yeah. Pattern center could be way up there or way over here somewhere.
Because it goes on narrow,
Mm-hmm.
and then
Yeah, yeah, it can absolutely be out of the field of view of your image. Mm-hmm.
If pattern center is out of the phosphorescence screen,
It could be.
it could be.
Mm-hmm.
So in that case, will we get the Kikuchi line or?
Yeah,
We will.
yeah, you can get good diffraction. I mean, if you just, the simple example that I used when we were talking about this earlier is if you have a electron beam and you have your phosphor screen over here and you have a working distance like this, then the normal to your phosphor screen is there. If you decrease your working distance, your normal to your phosphor screen's there. If you take your working distance way down here, the normal to your phosphor screen is here, right? But this is where the image is going to be, up here. So if you move the specimen around, you know, you could move it all the way through the field of view. But the main diffraction that you get after it hits there is going to be mostly down in this range, right? So your strongest diffraction is coming like this. So that's where you want to put the phosphor screen. So if you're way down here, you get your strongest diffraction down here. You maybe get a little bit up there, maybe see some pattern, right? And you'll see that as you move the working distance around, you'll see strong intensity at the top of your detector, at the bottom of your detector. And then you try and do a background correction to smooth everything. But if you just look at raw image, you'll see exactly if you're in the center with your maximum intensity or not. Eraser, let's see. Kind of.
Sir,
Yes, question.
sir, means for the pattern center, we have to take a specific band or we can take any bands? For we want to-
So the pattern center is determined independently of what the orientation of the crystal is, right? So I was just, when I was drawing it and doing it from the specimen, it's from a single pattern without knowing the pattern center, I was just looking at any bands. What I was trying to do is looking at the ones that were the most exaggerated, right? This one maybe I could have used where it's much wider here than it is down here. That's a smaller distance, right? And so I go to wherever it's smallest and take that normal. So I could have used any 2 bands or 3 bands or 6 bands. They should all fit right at the pattern center. Okay. All right, so back to the problem. Symmetry. So we said we see symmetry in the patterns. This one we've done already. This one we're looking at on the left side. So we said that was a 111, right? Which means these are all 211 types, these 3. This one, and one over here is all going to be a 110 type. Those are just zone axes. And so this is showing threefold symmetry. So these bands are all from the same family. These zone axes are all from the same family. Right, you rotate about this 120 degrees, it should look exactly the same. Now it's not exactly, you can see it's distorted, right? This line is, this line and maybe this line are longer than, well, let me see. This line here and this line here are longer than this line here, right? But that's because of the projection, how it's distorted. This one's going through the pattern center, these are away from it, so it's going to be distorted, they'll look longer. Okay, so knowing that's threefold, what about a mirror plane? Where can my mirror plane go? Say that again. So you're going, where do you want to go from? You want to go through the 111, right? So which one are you going from? 110 here or something? From this one? See where I'm scribbling here? Is this where you're going from? Do you want to go point at it or do you want to come scribble it for me? My poor class, I call people to the board all the time. Get up here, let's work it out.
So from 111 to 110, 110.
Okay. Mirror, mirror. Does everybody believe that? That means a reflection across that plane. That means this should be the same as this. And if I go out to this one, there should be another one of those out here, which maybe we can't see. Right? This one should have another busy one out here, which it is, right? That's 2110 types. So yes, this is a mirror. And so the fact that that's a mirror and the fact that this is a threefold symmetry axis, that means this is a mirror also, right? And this is a mirror also. Right? They're all mirror planes. All right. This next one is much more complicated. We're not dealing with cubics anymore. What do you see in there? Do you see any symmetries? Yeah, the one on the right, this one here with the X by it. Okay. I see one mirror as well.
Left upper corner to, you can see one.
Left upper corner, this?
No, intersection of those two lines, those two patterns. Left upper corner, two bands are there. Their from their intersection.
I'm looking. There's a lot of intersections. So, are you talking about this intersection? This intersection?
No, the one you left example.
This one?
From there, one mid line is coming.
Okay. And where are you taking that line to? Along here?
Yeah.
Okay. So if that's a mirror, that means this point has to be the same as one over here, right? You have 2 points like that. Here's the mirror line, so we need 2 over here maybe. And we would have to have, this line isn't normal, so we'd have to have another one like this. Right, so that's not going to be a mirror plane. Okay? It's hard to pick them out sometimes. It's hard to pick them out. And I'm drawing all over them, so. The wider band. Can you see my eraser up there? You can, right? Are you talking about this band? This? Okay. Let's draw that one in there and take a look. All right, so if we're doing a mirror, that means this zone axis should be similar to that, right? That makes sense. How about this one out here, this one out here, one here and here. This one has a little triangle, this one has a little triangle. That one seems to work, right? Okay, so this is a mirror plane for that. This point right up here is actually a 6-fold axis. We just can't see it. So these are parts of a hexagon, so we would draw the hexagon up around that. Okay. All right, what about this one? You see any symmetry? I love this pattern. It's a real pattern, but it's from a quasi-crystal. So it's not from any of the 7 crystal systems because it has a 5-fold axis. You can see the 5-fold axis in it. It has a nice 5-fold axis, which means all of these coming from the vertices, all of these are mirror planes, right? 5-fold axis, those all have to be mirror planes. So yeah, that's an iron-based quasi-crystal. I like that one. We'll skip it. We'll go to the next one here. I just like to show that because I went to the trouble of actually indexing that pattern one time.
But in 3 dimension, we cannot see 5-fold symmetry.
In 3 dimensions?
In 3-dimensional space,
It's 3-dimensional space, right? I mean, the diffraction's in 3 dimensions.
no, yeah, but it is projection.
It's just the order occurs over a short range,
Mm-hmm.
not over a long range.
Okay.
So the ordering occurs over a short range, and you actually get this 5-fold symmetry.
Okay.
Okay, what about the one here? What do you got? I didn't understand. Horizontal line mirror. Okay. Does everybody agree with that?
Mm.
The vertical line? Okay. So you have 2 mirrors that are perpendicular to each other, is that correct? So what does that mean?
Two-fold X. No, 4-fold.
4-fold. Right.
4-fold X.
So this is a 4-fold. This is a 100 type of a zone axis. And so if we look at 4-fold symmetry, we can look at a few things around here, but this zone axis and this zone axis, this zone axis, these all have to be the same as each other. This is trapezoidal instead of square, but that's because of our distortion in the nomic projection, right? Yes, good. Okay. So it's a good time for a quick break, I think. Is that right? Are we doing 5 minutes or are we doing 15 minutes? Last time we started taking a break and then we stopped and said, let's get tea, and so we started working again. You want to go check? Okay, we'll keep working. We'll keep working until the boss tells us.
Let them have.
Let's take the tea.
All right, so we're going to be looking at this pattern for our last exercise. And I said, let's draw 3 additional zone axes. We've been playing with this already, so this shouldn't be too hard now because we've been doing it already. And then we're going to do the indices of the lattice planes for the Kikuchi bands. We've done some of that. Then we're going to determine the specimen to screen distance. We've done that already, so that's going to be easy. And then for extra credit, we're going to get the orientation of the crystallite as a direction cosine matrix, which I'm not going to actually go through the entire calculation, but we're going to go through how you would do the steps to get there, and then if you guys want to go calculate it, you can do that. Do that for homework. Extra credit homework. I'll give you 500 extra points if you send me the solution and say it's correct. 500 points. I don't assign grades or anything, so points don't matter, but that's okay. 500 points.
Orientation of
What I tell my students is I give love points. These are points from the heart, right? These are love points. They don't count on your grade, but they count in my heart.
they will remain in the heart.
That's the most important points, those love points. Yep. Unless you're getting a bad grade and you need a few extra points, then other points are important too. Yep. Okay, keep working, Sonji?
Yeah.
Keep working? Okay. All right, so the first thing it says is let's do 3 additional zone axes and the axes of 3 Kikuchi bands. Now we know this is silicon calibration sample, and we've said the pattern center is at So what do we do? How do we get the information? How do we get more zone axes, and how do we get the Kikuchi band indices?
And symmetry.
You see symmetry? Okay, what symmetry do you see? You see mirror planes, you see 2, 3, 4-fold axes. What do you see?
Mirror plane is there. A vertical mirror plane.
Okay. So I heard a vertical plane for a mirror. I'll buy that. What does that tell you about the pattern? We have one zone axis that's off of that plane, right? That's that 011. And I put those as pointy braces, but I should have them as square braces because I'm going to insist that we have the right ones. So if that's a mirror, then this 011 has to be the same family as this one over here, right? Okay. What about this one? You see symmetry in that one? Okay. Threefold symmetry, is it consistent with what you think should really be there? We have a 114, a 112 on this same band. If that's a 111, is that still consistent?
It is 2 poles.
Maybe. How do you determine that? You have to determine what the band is, right? Anybody know what the band is off top, or do you need to do the cross product to figure it out? Because we know the cross product of 114 with 112 is going to give us that band. And we know that the dot product of the band with the zone axes has to be 0. So you can go to the zone rules or zone laws or whatever we call them. We call them 2 different ones, right? We had a zone rule and a zone law, something. Because somebody asked me the difference between a rule and a law, which I thought was good question. Just different people published it, I guess.
Is there any difference between rule and law?
Just whatever you want to say, right? When the policeman stops you and says you're doing something wrong, so I didn't know that was the law, I thought it was just a rule. See what they say. Okay, so did somebody do the dot product or the cross product, or somebody can figure it out just because 114 and 112 both have to be normal?
114 and 112 both has to be normal.
Or you can say, oh, this is that silicon calibration sample, so I know the vertical line is the cleavage plane. Do you remember the cleavage plane in silicon? Somebody's calculating, right? I'm waiting for an answer, so somebody's calculating.
Cross product is coming 2 to 0.
Cross product. Oh,
Yeah, 2 1 2 0.
what? Okay. And I don't know if you did 114 cross 112 or 112 cross 114, but you got 2. And where did you have a bar? You had bar 2 on the second one? So you can erase it so it doesn't look so crappy. Okay. All right, so if I do 114 cross 112, I get 2 bar 2 0. If I cross 112 with 114, I get 2 2 bar 0. Right? They're just negative of each other. It really doesn't matter which one we use. Okay. So we have to identify the plane. So the plane we're going to say is 2 2 bar 0. Other way, 2 bar 2 2 0. Okay. That's this plane. That's that mirrored plane. Okay. All right, so we're happy with that one. This we said was going to be a 111, and we asked if it was consistent. Somebody said it was a 111 zone axis because it was threefold, so that's again consistent with this. Dot product with bar 2 2 0 is 0 again. So we believe that one. So we've got an additional zone axis here. We've got a band. We know from symmetry that this has to be some type of 110, right? And we know from symmetry that this band has to be some type of 220. And the same with this one. So this one would be easy if we do 011, 111. Then what's the plane? Can you just tell me what the plane is if you know it's in the 220 family?
So now we can have a break.
Oh, now we're just so excited with this. Somebody give me this 220 specific indices and then we'll take a break. So I want to know the indices of this band coming through 011 and 111. Can you just tell me because you know it's 220 type? And we know the dot products have to be 0.
So that's 0 1 1, right?
This is 011, yes. Mm-hmm. So if we dot 220 with 011, is it 0 dot product? No. If we dot 202 with it, is it 0? No. If we dot 022 with 011, is it 0? If we put a bar somewhere, it is, right? So what do you want to call it? Yeah, 1-1, or we can do 2-2 because that's the diffracting plane, right? That's why we're doing 2-2 instead of 1-1. Yeah, yeah. Okay, so you want to put a bar on the second one? Good. I'm happy with that. The only difference is, are we doing, there's your plane. Are we looking at that normal or this normal, right? Either one are satisfactory for what we're defining. Okay. Good. Okay, we're gonna take a rest, big breath, and then we'll come back and see if we can get a direction cosine matrix. How long of a break? 10 minutes break.
I feel during EBSD.
So, Dave, I will take your leave and I will be coming in 1 hour. Kindly, if you could just
We're going to be a lot smarter 1 hour from now. We're going to be a lot smarter. Ready? Okay. All right, so we're back. We're playing with this problem that we were dealing with. We have labeled a few more zone axes. We have identified some Kikuchi bands. Now it's asking for the specimen to screen distance. So for that, we're going to go back to image J. Here's our pattern. We're going to take a measurement, and what measurement do I want to take to get a specimen to screen distance? This is just like you're doing homework, you're all sitting around. Okay, specimen to screen distance, what do we do? We know the pattern center is right there, where the 114 is. Right where my cursor is, that's 114. So what measurement do we want to take? I know some of you know, you're just being shy. Don't be shy. We've been together for, a couple of weeks, don't be shy. We can be honest with each other.
What is the question?
So to repeat the question, we're trying to measure a specimen to screen distance.
Okay.
So I'm going to measure something on my pattern to determine what my specimen to screen distance is. Right? That's something I absolutely need to know to be able to measure what the orientations are. So help me here find out what the specimen to screen distance is. What do I measure? I know that's the pattern center, 114. And we know the pattern center is normal, normal to the phosphor screen. Let's say this is phosphor. So the electron beam hits the specimen, right? So this is the phosphor, which is what we're looking at here. So we need to measure something on here to be able to determine this distance. So what is it?
You know, 114.
I see a few of you mouthing words like you're going to say something. Do we know the angle between 114 and 112 or between 114 and 111? Do we know that angle? Easy, right? Dot product. I mean, it took us about 5 minutes to get an answer of the dot product last time I asked for a dot product. But it's just a dot product that gives the cosine of the angle. Okay. All right, so if we go here from 114 and we measure to something that we know is a given angle away, right? Let's say that's right? So if those are the two I'm going to use, I'm just going to measure this distance here. between 112 and 114. All right, so I'm just going to do it here, just a second. So when you don't answer me, I'm feeling like everybody's lost and we should start over again. But we did one of these, you know, an hour ago, a half hour ago. So pattern center here. We're going to measure this line from here to here, which if I look up there, it says it's 90, 87, something, 88. I'm going to call it 88. So measuring from, oops, maybe that's a little long. Just trying to get a decent measurement there, just so we have a chance. Yeah, it's probably close. All right, 85 I'm going to call it. So this distance here between 112 and 114 is going to be 85. It's measured in pixels. I said on the problem to measure it in millimeters, but let's just do it in pixels. So if that's 85, we need to know this angle. Has anybody done this calculation for me yet? 15.
0.78.
Okay, 15.78 degrees. So if I know 85 is between 112 and 114, and I know this angle is 15.78 degrees, how do I determine this specimen to screen distance?
300.
Tangent 15.78 equals 85 over z star, right? You said z star is 300? Exactly 300? Close?
0.58.
300 point something. Okay, so 300 is good. All right, so we know z star. Now, next thing we want to do is we need to determine the angles between planes. In the coordinate frame of the phosphor screen, I'm going to pull up this just to jog memories. All right. So this is the position of the specimen of the pattern center. That's the bandwidth angle. We've done that already, right? So we measured where the beam came in from the pattern center, and then we measure this distance and this distance. We got the bandwidth angle. So we've done that. Now what we're going to do is in the coordinate frame of the phosphor screen, we're going to determine the position of these planes and their orientation. Okay. So now we know in this coordinate frame, phosphor screen, we know how far away the specimen is, and we know where that point is in the plane of the phosphor screen. So now we need points P and Q. So let's go back. Go back to our image J. And And this position says it is at x equal 226 and y equal 53. So let's take a note of that. So that's x star equal 226, y star equal 53, z star equals 300. So this is the pattern center in the coordinates of the phosphor screen, right? Okay. Now if we come, we have to choose one of these bands that we know the Miller indices for. So we said we knew Miller indices along this band, for example, right? Do you remember what they were? We wrote them at the top of this page. Okay. Bar 220. Okay, bar 220. Now we need 2 points along here to figure out the normal. Do we really need those 2 points? We've kind of lined it up so it's exactly lined up, and we know the normal is going to be right. It's right on the pattern center. Pattern center includes that line. So the normal direction is going to be pointing out this way. And if we do that in this coordinate frame that we're looking at, it's just going to be vertical. It's just going to be lined up. So it's going to be a 0 component in Z from the phosphor screen coordinate frame, a 0 component in Y, and 1 in X. Right, so we don't even have to do this cross product. See how I'm cheating on that one? Right? So let's cheat on that one. So this 220, bar 220, in the phosphor coordinate frame has a normal, which we're going to call N1, and it's going to be 1, 0, 0. I can put commas there because it's just a vector. Right? Does everybody see why we did that? The next one we're going to have to take and actually measure these. So let's do this next one here that we identified, O2 2 bar. We're going to call that N2. And then we have to come and actually take some measurements. So let's measure a point maybe on this side and on this side of the zone axis. Okay. So I'm going to come up here somewhere. Just trying to be in the center of that Kikuchi band. And it gives me 433 and 120 for X and Y. So 433, is that what I said? X, 220. So that's X and Y. And then, so that's one point on the end and a point on the other end. So that's like taking a point right there. Now we're going to take a point right here. Let's go measure that. Put my cursor there. It's now telling me 81 and 372, right? Oops, it's not 37 squared. Okay, so that's the XY points in that frame. Now, what we need to do is take this. I'm going to just bring this up and kind of put it on the side. What I've got to do is minimize this one. Not minimize, but make it so we can play a little bit. Yeah, almost. Okay. Okay, so we're taking this thing. Bonk. Taking this thing and we're saying we have a point P and a point Q. Where's the point 0? Where's that origin point? That's this, right? That's the pattern center, exactly. Okay. So we're measuring that pattern center. We're saying Z is 300 away. And so the Z on both of these has to be 0. Right? We're in the 0 plane if we're saying that the Z where the beam hits the specimen is 300. So these Z's are going to be 0. All right, so if I have the vector that we're going to call OP is going to be defined by uh, 2, 2, 6. Let me see, let's maybe put a P up there, and we'll put a Q here. So this will be P, and this will be Q, right? So OP vector. How do I know a vector between points if I know 2 points? Just subtract them, right? Okay. Does it matter which way we subtract them? As long as we're consistent, it'll give us a normal plus or minus is what it will do, right? So we're going to have 226, 53, 300. And we're going to subtract that from 433, 220, 0. And 207, right? How about the next one? It's going to be 167, is that right? Okay, you guys check me, right? So I'm making sure I'm doing this correctly. Okay, for the second one, OQ, we're doing the same thing, and I'm going to squeeze this in under here. And OQ, Q we said was 81, 372, and 0. So we're going to subtract the pattern center. We're going to scribble this in at the bottom. So I have 81 minus 433, 352. Is that right? 372 minus 220, 252. Dankeschön. Glad people are watching. Good. And then I did something wrong. This is 300. 300.
This is OQ or PP?
81, 372, 0. What did I do wrong up here? 81, 81. Thank you. Thank you. Let's just erase this. Just ignore all this stuff. Oh, whoops. So I didn't use the pattern center. I was doing P from Q, right? So just ignore this. See, that's why you guys are here, to make sure I don't do this kind of stuff. All right, so now we're going to do this pattern center 226, 53, 300. Then we're going to minus from 81, 372, and 0. Right, so it's just the 2 points on the line. We're taking the two vectors, subtracting it to get that vector. Okay, 226 minus 81. It's 100 and something or other, 45 maybe. 53 minus 372, that would be 319, and then 300, right? Okay. So now I have two vectors, OP and OQ. So if I come over here, I want to find the normal to those two vectors. I have to take the dot product, or the cross product, I'm sorry, right? And that will give me a normal in the coordinate frame of the phosphor screen. And I already know what the normal is in the coordinate frame of the crystal, right? Because it's a 220 type. Because we selected it specifically to be I think we're doing this one, the O2 bar 2. Right, so we have the first normal. We did that just because we could cheat on the geometry. And the second one we need to calculate from this cross product OP cross OQ. Okay, anybody want to do that cross product? Does anybody have a cross product calculator up? I see somebody working hard on the calculator, so we'll wait a minute. OP cross OQ. That's going to be this vector cross this vector. See, this is all just geometry and bookkeeping, right? It's not rocket science, really difficult kind of concepts. It's just geometry and bookkeeping. I like it. He was not happy with the geometry problem. Started growling. Okay, so we're at 11 o'clock. So right now we're in the middle of that problem I said is extra credit. And we've showed you how to get N1, and you do a cross product and you get N2. After that, you will determine the angle between them if you want. You don't really need to on this case because we already know it's a 220 and an 022. Right? We know exactly what those bands are. We've said right here, bar 220, right here, and 022 bar. We have this in the specimen, in the phosphor coordinate frame. In the notes, I called that E sub P. If we come over to this, right? We call this E sub P. Wow, nice. Called that E sub P, so we can use N1 and N2 to define this coordinate frame. The crystal frame we already know about because it's HKLs. So this we can get, this we can get. And then we have only this difference between the specimen and the phosphor screen, which is a 20-degree rotation, which we can do the direction cosine matrix immediately. And then we have everything, we can calculate the direction cosine matrix. It's messy to do by hand, right? The computer does this 8,000 times a second or whatever, and so we don't need to do it. But to do it by hand, a little messy, but it's nice to know exactly what's going on with the calculation. All right, so since this is the extra credit problem, I'm going to leave it for you. And if there's any questions, I'll take them quick before we turn the time over to Dr. Banerjee.
N1 cross N2 will be in the plane of the phosphorus.
N1,
Cross N2.
N1 and N2 are in the coordinate frame defined by the phosphor.
Okay.
And then we create an intermediate coordinate frame that we're calling this EP. This E hat P is an intermediate coordinate frame that we create from a knowledge of the normals of the planes that we know in both the crystal frame and in the phosphor frame.
Okay.
Right, so we know where our specimen is, we know where our phosphor is. The crystal we know, and we can create something from the phosphor frame, the exact same representation in the phosphor frame coordinates as well as the crystal frame coordinates. And from that we can pull out our direction cosine matrix that gives the orientation of the matrix, of the lattice.
So N1 N2 are in the sample coordinate system.
So N1, N2, the way we're defining it here, the way we did it on this graph, this is in the coordinate frame of the phosphor screen, but we know these bands are 220 types. So we know that's an O bar 22 and that's a 2 bar O, something like that. So we know both of those. So we know exactly in the coordinate frame defined by the crystal, we also know those. And then we know the relation between the specimen and the phosphor just because of how they're rotated with respect to each other. So that's the math that's being done here to find the final direction cosine matrix. Okay, so it's just multiplying some matrices and doing some cross products, and you're there. Okay? Final question? All right, it's just math. It's just easy math. No tensors, just cross products, dot products, you're there. All right, thanks guys. Next time, tomorrow, if you have a laptop with OIM analysis on it, then you can follow along and play with what I'll be doing. So it'll be useful if you have that. All right, Professor. I'll close out of all these. I think I can eject this. Wow, nice, that worked. That image J, I wasn't sure if it would work from my flash drive.
Oh, okay.
It's a high quality program. Do you guys use image J?
Sorry?
Image J, you know that
Yes,
code?
yes, software.
You guys use that? Yeah.
Right? Yes, everybody knows.
HDMI. No worries. Trying to find the HDMI here. ওইটা বের করে এখানে লাগে
না এইটা না না
এখানে কিছু দেখছি না Okay, welcome to the fourth lecture in this series. Today, as the title suggests, we are going to explore density functional theory as an approach for solving problems. It's an interesting topic, and in the sense that density functional theory is a quantum mechanical solver, essentially, right? And I haven't introduced quantum mechanics at any level in the past lectures. So what I will do is I'll start out discussing the fundamentals of quantum mechanics in briefly, because by itself quantum mechanics is a whole course, right? So I'll just introduce it to the appropriate level to appreciate the solution of these problems with density functional theory. So the field of quantum mechanics evolved, as you know, towards the beginning of the 20th century with Planck's law is pretty much the centerpiece of it, where electromagnetic radiation was discussed, and theoretically was seen that it happens in packets of energy. Only quantized versions of energy is absorbed by chemical species or atoms. With the advent of that, there was a lot of work put together from looking at various aspects of it, looking at the dual nature of electromagnetic radiation, it behaves both as particles and waves, and also looking at matter waves, that is electrons, protons, etc., and their wave-like characteristics. So if you think back to the beginning of the 20th century, most of the eminent scientists that you can think of, Erwin Schrödinger, Max Planck, Niels Bohr, de Broglie, Lorentz, Einstein. I mean, there's tremendous amount of contribution to this field and in developing the theory. So the centerpiece of this is, again, thinking of radiation from a quantized sense, that it doesn't have mass, but it does have a momentum, and you can define let me get my So you can think of electromagnetic radiation. Okay, should have probably put it up. Give me a moment to connect this. Why doesn't it like my pen stylus here? Was that?
Did I break it?
Nope. It doesn't exit the full screen mode for me for some reason.
Tab, if you press tab.
Yeah, I'm just trying to escape from the full screen mode to set up the stylus, but it wouldn't let me do that.
Did you press tab
Course.
button?
Yeah, I did. So let me just do something here. I'll disconnect this and connect. Yeah, now it recognizes, I think, but still doesn't let me edit. Had no problem before.
Yeah, someone looks
Why is it not recognizing it?
Call somebody from here.
I would like to be able to mark here. Full screen mode I cannot exit the full screen mode for some reason.
Right, full screen থেকে exit.
To be able to edit this or mark here. This is a bit of a problem. Should I try to disconnect and connect? Yeah. Right. Sorry. Okay. Now it's,
Maybe that or that interface problem.
yeah. Just trying to reconnect it. Sorry about the technical issue here. Okay. It's been working.
Slowly, no problem.
That's kind of strange.
Just to restart the system, sir.
I guess that's what is left to be done here.
Somehow it got done.
It just doesn't
Restart
escape.
it, why it is still there? Should not be there.
I'll probably just restart my computer here.
Restarting is the
Some problem.
only one.
It's just locking the screen. Pen settings. Maybe now it'll work. It doesn't? Just hold this down.
Close the program and restart.
Yeah.
Same thing happens to me when I start talking about quantum mechanics.
The electrons are not cooperating. There you go, right?
Probably.
Okay. Hopefully works now. Okay. Picture slides. Okay. Now. Draw. Use a marker. Do this. Okay, just to restart. Now it should come up there. Okay, so let's continue with the discussion. So we are talking about the dual nature of electromagnetic radiation as particulate as well as a wave versus that of matter. So de Broglie came up with the idea that that of matter waves. Basically, if you take electrons, protons, any particulate matter, you can associate it with a wavelength that is given by the Planck's constant h over the mass times velocity, basically the momentum of that particle, which obviously at the continuum level, because the Planck's constant is a very small number, doesn't matter because it will lead to a wavelength that is almost infinitesimally small. But if you go down to very tiny particles such as an electron, then you observe finite wavelength, and you can associate, for example, a narrow beam of electrons with wave-like nature. And this was confirmed from experiments in the 1920s where a narrow beam of electron was passed through a thin metal foil, very famous experiment, and diffraction behavior was observed. So at that point, there was a lot of interest in coming up with a model for the atom, and the simplest atom and the simplest model is based on Niels Bohr's theory for an atom such as hydrogen, which is pretty straightforward. The idea is we visualized atoms as with a nucleus and electrons spinning around it or orbiting the nucleus under a Coulombic potential, much like the potential that I discussed yesterday for interaction of charges in molecular dynamics simulations, right? It's a product of charge over the distance with a prefactor. So based on the experiments and absorption of energy, it was deduced that electrons can only revolve around the nucleus with certain discrete values of angular momentum that is given by a constant number times the Planck's constant over twice pi, and that number is famously called the principal quantum number. Okay? So this is a very simplified theory that explains or helps us understand the behavior of simple atoms such as hydrogen, but it still doesn't capture a lot of the complex physics that is observed from experiments. And to kind of account for that, other quantum numbers such as the azimuthal quantum number, the magnetic quantum number, and spin quantum numbers were introduced. So now you can think of the atomic system and the electrons and the electronic behavior in terms of discrete quantum number, including the principal, azimuthal, magnetic, and spin quantum number. That describes kind of the shape of the orbits. They are not necessarily spherical, so you can come up with ellipsoidal shapes of the orbits of electrons around the nucleus. But it's still, Niels Bohr's theory is still insufficient to describe complex atomic structures. So to do that, at that point, mathematically, Erwin Schrödinger formulated the most important governing equation in the domain of quantum mechanics, which is named after him as the Schrödinger's equation. The derivation of this equation is actually not very complex. You start with a standard wave equation, like from a string vibration. Let's say you think of a vibrating string and develop the governing equation for the vibrating string. Now what you do is, instead of the vibrating string, you think of de Broglie's matter waves, which has the same wave-like characteristic as the vibrating string. So you replace some of the potential or energy term with that for de Broglie's matter waves, and that yields this governing equation, which is called the Schrödinger's equation. So the big question is, what are these variables? There is a potential. It's a very generic equation and can be applied to pretty much all particles, any particle that you're interested in modeling, or you can apply it to atoms as well. So this quantity phi itself is a potential for defining the interaction between the particles that you're trying to model. The energy epsilon as we will find out, can only have discrete values. It's the total energy of that system, and there is this variable psi. So, what is psi? It's called the wave function. Psi is the wave function, and by itself it's very difficult to think of it in a physical term, right? By itself, psi actually could have both real and complex solutions from if you solve this Schrodinger's equation. So, it's very difficult to think of it in a physical sense. But what is true is there are some constraints. You can think of psi or a function of psi as a probability density function that describes the location, if you are thinking of an electron or an atom, the location in space of where that particle can be. Permissible locations is based on the solution of psi. But not directly, because like I mentioned, psi can have real and complex solutions. What we can do though is we can come up with the product of psi and its complex conjugate and give it some boundary conditions or constraints such that it has to be single valued, continuous, differentiable and square integrable. If you impose those constraints on psi, then the solution that you have, which is the wave function psi multiplied by its complex conjugate, can be likened to a probability density function for finding that certain particle in a space. The space we are looking at in 3 dimension is, this is kind of, you can think of a small domain, x to x plus dx, y to y plus dy and z to z plus dz, and this quantity tells you the probability of finding that particle in that domain, and therefore if psi square times dx dy dz is the probability of finding a particle in a domain of space, then psi square itself is a probability density. Okay? You normalize it with the volume. So, Schrodinger's equation can be solved for simple systems. By the way, this form of the Schrodinger's equation is called the time independent form because you do not have the dynamics that is captured here. So, this is just thinking of the stationary modes of a string vibration, for example, which does not have time involved in it. So, this is a time independent form of the Schrodinger's equation. It is still a very complex partial differential equation. So, it can only be solved analytically for very simple systems such as a particle in a box. You can solve it for harmonic oscillators, which can mimic the behavior of a diatomic species, let us say an oxygen molecule that is vibrating. So, you can capture the vibrational modes through a harmonic oscillator, or you can solve for solve the Schrodinger's equation for rigid rotational modes of degrees of freedom. And what you find from it, which I will show you for a particle in a box, is that this equation can only be solved for certain discrete values of energy epsilon. So, you cannot solve it for any value of the energy epsilon, but only discrete values of energy epsilon would lead to these conditions that the solution psi will be a single valued continuous and a differentiable function. Okay? So, those are important constraints. Let us look at an example. The simplest example is a particle in a box where you can actually solve it. But before, well, let us look at that first and then we will come back to the slide that I just put up. So, let us think of a 1D solution to the Schrodinger's equation for a gas atom that has only translational mode. We are not thinking of interaction between the particle and another particle. So, it is kind of an independent particle that is translating between this domain in 1 dimension, and we will extrapolate the solution to 3 dimension afterwards. So, in the 1 dimension, this particle is constrained to be within these 2 domain lines x equals 0 and a certain dimension x equals L. So, it has to be located within these 2 walls. How can you think of that? How can you kind of convert that mathematically? Mathematically, if you set the potential phi x to be infinitely high at x equals 0 or x equals L, that just means you have a hard boundary. The particle can go beyond the hard boundary at x equals 0 and x equals L. On the other hand, at any location of the particle between these 2 walls, x equals 0, x equals L, the potential can be 0. Why? Because this particle is independently moving around and it has only 1 dimensional kinetic energy because of its motion. So, if you introduce these constraints on the system to describe its behavior, then this this differential equation, Schrodinger's equation in one dimension turns out to be a ordinary differential equation. Okay? This is one of the simplest formulations of it, with the boundary condition that if psi is a probability density ultimately, or psi square is a probability density, then you say that at x equals 0 its value has to be 0, and x equals L it has to be 0, because it can't go beyond the bounded domain of the box or this line. So, very quickly, if you solve this differential equation, the solution is pretty straightforward. It's like it's got this sine cosine solution with two unknown constant C1, C2. It's just a solution to an ordinary differential equation. So, if you set the first boundary condition that psi x at x equals 0 is 0, automatically the constant C2 turns out to be 0, unless you want a non-trivial solution. We want a non-trivial solution, so C2 is 0. Now, the other boundary condition, which is psi x at x equals L is 0. This should probably, so even though I wrote L, let us say this is uppercase x, okay, because I think in the solution I am just, instead of L I am using uppercase x as a dimension. So, if you do that, then this is what you get from the boundary condition. Again, one trivial solution could be that C1 equals 0, but we do not want a trivial solution, because in that case the wave function will be 0 at all locations. So, if you do not want that, then sine function of this quantity in the parenthesis or brackets is 0, meaning the solution is x times square root of 8 pi square m times the energy over 8 square has to be an integral multiple of pi. Okay? So, this quantity k x is basically a quantum number, and its permissible values are 1, 2, 3, 4, etc., integral values. So, what does that tell us? That if you take this equation and kind of substitute k x equals 1, 2, 3, 4, what happens to the energy? You can express the energy here as from this equation to have only specific values. It cannot be a continuous function, it has to have some discrete values based on this condition. Okay? Also, each of these quantum numbers, or each of these values of k x, let us say k x equals 1 or 2, will be associated with a certain solution to the Schrodinger's equation in 1D, and that solution will be a sine function. Okay? So, we have from solving this Schrodinger's equation, there will be only specific quantized values of energy, and each of those energy will be associated with a solution which is given by this wave function. You can find the value of the unknown constant C1. How do you find the unknown constant C1? By recognizing that if psi square is a probability, then if you can integrate that probability function from x equals 0 to x, what is the total probability going to be? 1. So, basically you are normalizing it, and when you normalize it, you get a value of the constant C1 as square root of 2 over x. So, basically the solution that you have is this. So, obviously this is not one solution, this is a series of solution which depends on that quantum number k x. So, how do we extend this to 3 dimension? You can think of now the particle being, instead of moving along one dimension, the particle moves in a box of dimensions x between 0 to uppercase x, y remains between 0 to uppercase y, and z remains between 0 to uppercase z. So, now the particle is moving in this box between 0 to x, let us say this is 0 to z, and this dimension is 0 to y. Okay? So, if you just extend that, the energy of this moving particle, translating particle, will be the sum of the energies in the 3 discrete dimensions x, y, z. And again, if you revisit the solution that we had earlier, you can show that the discrete energies of these particles are a function of now the 3 quantum numbers. Remember, now we have 3 quantum numbers, one in each dimension, and is given by this function. So, and the wave function, corresponding wave function, is given by this expression as a sine function of each of these dimensions. So, the simplified situation is if you are considering a cube where x and y and z are equal, and each of them are equal to 1 cube root of the volume of the box, because if it's a cube, then x, y, or z are equal and they're equivalent to 1, the volume's cube root. Then you can express the energy levels or energy values that are permissible for this particle in a box with this function. So, what do you observe in this function? Number one, you observe that the permissible energy levels depend on the volume. This is something that I mentioned loosely when I was discussing statistical mechanics, that the boundary condition, for example, the volume of the system, determines what are the quantum states. And now you can at least see an example of it, a simple example, that if you have a particle in a box, then indeed volume plays a role. If you change the volume of the box, that changes the quantum states that are available for this particle to occupy. The second aspect is it also depends on the square of these 3 quantum numbers. So, let us think of a situation where kx is 1, ky is 1, and kz is 2, right? A combination of the 3 quantum numbers. Now, if I think of another situation where kx is 2, ky is 1, and kz is 1, so what happens to the sum of the squares? It remains the same, nothing changes. So, the energy that we get for that particular a different quantum state, this is describing one quantum state, and these 3 coordination numbers are another quantum state. You can think of it as coordinates, right? We have 2 coordinates, 2 distinct quantum states with the same value of energy, right? And what do we call it when that happens, when we have multiple quantum states with the same energy? Degenerate states, right? So, we saw a lot of examples of those boxes when we were discussing the statistical mechanics, and we looked at energy levels with degenerate quantum states, and this is a very simple example of how that happens. So, basically you can think of the Schrodinger's equation as a governing equation which when you solve, you are able to actually calculate all those quantum states that we have so far been assuming to be a certain value. We did not get into the physics of it. We were just looking at the math of it and kind of analyzing it to calculate various properties based on the most important variable in statistical mechanics that we discussed, which is the partition function, right? We looked at partition function, which basically is a function of all the quantum states and the energy levels available to the system, and now we are discussing a tool where you can actually calculate each of those energy levels and the degeneracy, which is important for calculating the partition function. So, if not anything else, that itself is a very strong reason for kind of solving this equation, but unfortunately, like I mentioned, mathematically it can only be solved for very simple situations. If you are interested in visualizing the solution that I just showed you in the previous slide, I have 2 graphs here for the 1D situation. You can extrapolate this again to 3 dimensions. So, the left plot here shows you some of the modes, some of the 3 wave functions for kx equals 1, kx equals 2, and kx equals 3. So, what we are looking at is the wave functions themselves for the first 3 quantum numbers from the previous solution, all sinusoidal, right? Now, again, there is no physical, easily understandable physical variable that you can assign to these solutions, but you can assign probability density to the square of the wave function. So, let us look at the square of the wave function for a particle that is moving in a 1 dimension, and you get these 3 solutions. It is basically taking these functions and finding the square of it. So, what do you observe? That if for the lowest energy mode kx equals 1, this is the probability density for this particle to be located anywhere along this line, which is not uniform. So, if you did not know much about it, if you just thought of a particle translating in 1 dimension, your intuitively you would feel that it can be anywhere with almost equal probability. But that is where quantum mechanics can be counterintuitive, that what you see is there are only discrete locations where the particle can be with different probability densities. For example, for kx equals 2, this is how the solution looks like. So, the particle essentially cannot be present here. It has a 0 probability to be at the midpoint in that energy level. And then you can plot higher levels such as kx equals 3, 4, etc. So, this is kind of an example of a solution of the wave function. Questions?
How many solutions?
Oh, there can be infinite number of solutions, right? Kx equals 1, 2, 3 and you can go on. But you know, there will be the energy difference between each solution is not linear, and this is just the translational piece of it. But if you go to rotation, vibration, they're typically not linear, so the higher excited modes are less likely to occur. Okay.
So in that boundary condition for one-dimensional, you know that for between 0 to L, the probability of finding electron, it is mostly determined by the psi function or the psi square function.
The psi square function.
Then psi is basically the wave function associated with the electron flow.
Right, it's the wave function, but by itself there is no physically ascribable parameter to it, but the psi multiplied by its complex conjugate, the psi square, that is associated with the probability density, which is physically meaningful. By the way, this is not necessarily an electron because it is not moving around under a potential here. I mean, you just have a particle without an applied potential and we are modeling its motion. If it was under an electrostatic field and it was an electron, then we have to add that specific potential and solve for it. So, here we are basically assuming there is no externally applied potential for this particle. Please proceed, you had another question.
Sir, 0 to x in that equation, sir, between 0 to x, the phi x is 0.
Mm-hmm.
There is no potential.
There is no potential that we are modeling here. Okay. So, this is really simplified, you can appreciate that. Now, if you have multiple particles and they were interacting, this governing equation would look a lot more complex and it gets extremely challenging to come up with a closed form analytical solution for this equation. Even in 1D and 3 dimension, it becomes, you know, so it's a very challenging equation. I do have solutions for the harmonic oscillator and rigid rotator, which is mathematically pretty complex. The solution is a series solution, something called a Hermite's polynomial, and I will not present it here, but if you are interested, I can share those solutions with you. If you are interested to look at what is going to be the energy modes for rotation and vibration that you can use for calculating the partition function. It's just not very straightforward. Okay, so speaking of the internal modes, so this was just translation, right? If you have a diatomic molecule or a molecule like water, as we know, there are many internal degrees of freedom. So, how do we solve the Schrodinger's equation and come up with the energy levels and degeneracies for those internal modes? In principle, we can think of it in a simplified manner. The total energy of this, let us say if it is a molecule, will be its translational energy, and we can decouple it with internal modes of its internal modes. And the corresponding wave function that solves for all these modes is multiplicative. So, it is the wave function for the translational mode multiplied by the wave function for the internal mode, whatever that internal mode is. And we can essentially write separate governing equations, the Schrodinger's equation, for the translation and for the internal modes. For example, for translation, we can write it like this, where instead of, if you have a kind of a multi-atomic molecule, I mean a diatomic, triatomic, then we can model the translation or the kinetic energy for translation in terms of the location of the center of mass, and you know, we get an equation that is pretty similar to the one that we just solved. As for the internal modes, this is how the internal modes will look like, but there will be this potential phi in general will not be 0. For example, if you have a vibrating spring, a harmonic oscillator, there is a potential associated with that harmonic oscillator, and you have to introduce that harmonic function as this potential field under which the particle is, or in this case the pair particle that is interacting, and that will lead to a fairly complex solution. but you can still solve it. And once you solve for all those discrete modes, for example, the rotation, the vibration, the electronic ground states, your total internal energy for that particular system, for that molecule, will comprise of each of those components, the rotational, the solution that you get from solving the rotational modes, the vibrational modes, and if it is an electronic ground state, there will be some energy associated with it. Similarly, the composite wave function for this complex molecule will be a product of the solutions for rotation, vibration, and electronic ground states, and then you can connect it with the overall wave function. So, I am just kind of giving you a general workflow of calculating the partition function for a complex structure, molecule, let us say. Okay? If you are thinking in terms of a metal, then the only modes perhaps you will be interested in is the vibration. There are various ways you can model a metal, but you will be certainly interested in the electronic states as well. So, what you appreciate from this perhaps is it is not straightforward to solve this governing equation for a much more complex system, a crystal structure or a polymer. Solving this is pretty much not feasible. So, you will have to make some approximations and come up with a method to solve the Schrodinger's equation in a different form to get all the energy modes that you, or the modes that you are interested in. One brief aside, I want to connect the quantum mechanics discussion here with the statistical mechanics we discussed at length on Tuesday. So, how do we do that? One simple way of thinking is symmetry characteristics and distribution. Okay? So, think of two identical particles, could be a pair of electrons, pair of protons, or pair of atoms, hydrogen atoms, and let us say there are two quantum states available for these two particles to occupy. We call those quantum states I and j, and both quantum states are associated with a certain energy value. So, let us say the energies for those quantum states are epsilon I and epsilon j. So, then if you distribute those two particles in those two quantum states, what is going to be their total energy? It is just the sum of these two energies, right. At this point, something called exchange degeneracy comes into play. So, we have now thought about distributing the two particles 1 and 2 in those quantum states I and j, but which particle goes to what quantum state and what is going to be the wave function associated with that quantum state. So, let us say the wave function associated with the quantum state I is psi I and the quantum state j is psi j. Okay? So, like I said, the overall solution to the Schrodinger's equation, because it is a probability density, is multiplicative. So, we can think of a situation where the particle 1 is in quantum state I and particle 2 is in quantum state j, but it could also be that particle 2 is in quantum state I and particle 1 is in quantum state j, right, the opposite. So, both are feasible mathematically. So, what do? We realize at this point that actually we have been calling these particles 1 and 2, but in quantum mechanics all these particles are indistinguishable. We really cannot have a marker for them, right. So, how do we account for the solution where these particles can hop from one quantum state to the other? So, the simplest way of thinking about it is if these two are separate solutions, then we can come up with combinations that are also going to be solution to the Schrodinger's equation. One combination is a symmetric looking function, which is this psi I 1 psi I j 2 plus the opposite when the particles have exchanged their quantum states. The other solution can be anti-symmetric, where instead of a plus we have a negative in the function. Okay? But there are some rules at this point that we have to think of when we assign a particle to be either in a symmetry state or an anti-symmetric state. Okay? So, for the symmetry state, when we interchange the coordinates of the particle, it does not change the sign, but for the anti-symmetric state, we have a sign change. So, what we learn from this is if it is a symmetric, if a particle follows symmetry behavior, then we can easily interchange their state, and this can be not just for two particles, we can extend it to 100 particles. On the other hand, if a particle is following an anti-symmetry behavior, then, and we have 100 particles, as soon as we say that two of these quantum states available are identical, then this does not work out, right. So, all the particles have to be in separate quantum states if it follows antisymmetric wave function behavior. So, that is where we come to, we can now classify particles as those that have half integral spins such as electrons, protons, nuclei of odd mass number, and these particles follow the Pauli's exclusion principle, which basically says that these particles cannot flock to the same quantum state. They have to be in distinct quantum states. And therefore, now we know already from statistical mechanics, these particles that follow the exclusion principle behave as fermions, and then they follow Fermi-Dirac statistics, and we can use Fermi-Dirac statistics to derive their properties. On the other hand, we have particles with integral spins such as a photon, nuclei of even mass number. For those, they follow symmetry wave functions, and the statistical mechanical rule that we have to apply to evaluate thermophysical behavior of the collection of those particles is through the Bose-Einstein statistics. So, this kind of connects the quantum mechanics that we are discussing here with the statistical mechanic principles, because we know that each of those distributions are different. If you wanted to calculate the entropy of a collection of electrons, you have to use the Fermi-Dirac statistics and the expressions thereof. Okay.
So this is the particular reason why the electrons have upspin or downspin.
Right.
Because of the asymmetric.
It's plus minus half, and so for those particles, the electrons, they have to follow the antisymmetry wave function characteristics, which in turn means that we have to treat them as fermions fundamentally.
Plus minus, is that the Pauli's exclusion principle?
Pauli's exclusion principle is that all 4 quantum numbers that describe that electron cannot be identical, because then that would mean that multiple electrons can occupy the same quantum state. So, they can have the same principal azimuthal magnetic quantum number, but the spin state then has to be plus minus half, which is distinct. Okay, so now that we have realized the mathematical complexity of it, let's come to density functional theory. The precise reason density functional theory was developed because it's so difficult to solve the Schrodinger's equation for most systems that we care about in material science and in chemistry, right? It's just simply too complicated to solve these. So therefore, in the 1950s and 60s, there was a lot of work to see if we can model multi-electron systems somehow in a simplified manner, and these systems a lot of times assume the electronic ground state, and we came up with what is the key principle in density functional theory, which is the Hohenberg-Kohn theorem. Okay? The Hohenberg-Kohn theorem assumes that the ground state energy of a finite system is a function of the electron density. There are these postulates in Hohenberg-Kohn theorem, and that we can solve for many electron systems using functionals of what is called an electron density. So, that is how we can describe these systems, and the electron density that minimizes the energy of the overall function is the ground state electron density. So, applying these principles and extending them through the Kohn-Shams theorem, and the density functional theory was developed. And density functional theory, basically the underpinning assumption is a system of these independent non-interacting electrons can be used with a common one body potential that includes exchange and correlation to model multi-electron systems. Okay? And this potential models the same electron density as a real interacting system. So, these are kind of assumptions, truly speaking, and there are situations these assumptions will not be valid, but they are pretty generic, and we can apply these assumptions to solve multi-electron systems with density functional theory. What sort of material systems or what sort of physical processes can we model with density functional theory? Yeah. Sure. So, exchange and correlation is the behavior of the electrons in the system, multi-electron system. I can show you some examples of density functional theory where you apply different exchange correlation functions. Right. LDA is the simplest. So there are various models to look at the exchange correlation function. There are many other things that are not involved in here. For example, one of which is the dispersion term in density functional theory. Typically, you don't account for dispersion, but you can introduce dispersions or van der Waals interaction if you wanted to, especially if you're looking at carbon-based systems like organics molecules. Yeah, then you would introduce those dispersion terms. So this is a very simplified model. There are many different offshoots to account for more complex situations, relativistic effects, and I'm not getting into specific systems, but this is
Previous. That the exchange include exchange and correlation.
Mhm.
That you are talking about the parallel exchange, anti-parallel non-exchange.
Right.
That-
Sir, in this cone sums theory, basically in case of lattice structure or solids, some materials, we have crystal structure. So this includes non-interacting electrons. So in that case, if the atom is in lattice system, so they are interacting in nature.
Mhm.
So how do we bring the cone sand to that lattice system?
So you can separate out the nuclear behavior with the electronic behavior. If you are particularly looking at dynamics of this system, then there is Born-Oppenheimer postulate or assumption that you can make, that you kind of separate out the solution for the nucleus with respect to the solution for the electrons of the system. You can solve them independently.
Sir,
Yeah.
in the previous lecture,
Mhm.
no, so in which you are explaining addition and subtraction of wave function.
Mhm. Oh, okay. Symmetry characteristics here.
Also in this, so basically in the top one, all the electrons are having same spin.
We are not necessarily talking about electrons here. We're just saying, there are two particles and there are two quantum states that they can occupy. What are the rules for these particles to occupy these quantum states where we can think of the exchange degeneracy? And there are two ways that can be done. Like I mentioned, if you assume that any quantum particle is indistinguishable, so you can come up with these composite solutions to the wave function for a two-particle system, but then it can also be extended to more like multi-particle system. It doesn't have to be two. This is just an example. And you can do that in terms of either symmetric solutions or anti-symmetric solutions. In the first case, the sign doesn't change if there is exchange between two particles, could be two electrons. In the second case, the sign changes, which is we know is true for electrons. So what we, from this, what we deduced is there can be situations, there can be particles that follow symmetry characteristics, if that, or particles that follow anti-symmetry wave function characteristics. If that is the case, now if you have 100 particles, let's extend this, and if two of these quantum states are identical, let's just assume that's the case. If two quantum states, instead of, we are talking about these as quantum states. And how are these quantum states described? They're described with a set of quantum numbers. You can think of them as coordinates, right? Let's for the moment assume that two of these quantum states are identical. Then what we are saying is that two particles can move from one to the other, they can interchange. But on the other hand, if that happens, then you don't have the anti-symmetry behavior captured because of this negative sign if two of those quantum states are identical. So therefore, what we deduce is for anti-symmetry characteristics, none of the two quantum states can be identicals, which is the Pauli's exclusion principle, and particles such as electrons that follow that, therefore, have to obey Fermi-Dirac statistics, which is the assumption we made in statistical mechanics, that all particles are indistinguishable, and the other condition is that no two particles can occupy the same quantum states.
So if you consider phonons, so which
Phonons follow the Bose-Einstein statistics. So yeah, you can flock them together. If you're interested, there's some nice derivation for a box of, a box that is being irradiated by phonon, and you can think of the equilibrium statistical mechanical distribution of a collection of phonons, from which you can actually see the black body radiation distribution, that function. So you can derive that. It's pretty interesting.
I have a question. You have mentioned particles with half integral spin and particles with integral spin. So what is
So
the
half integrals, yeah, that's a good question. So half,
how can you measure that half integral?
so half integral is half 3 over 2. I mean, I'm not saying 4 over 2. 4 over 2 becomes 2, so it's an integral spin. So the spin states for that system.
Kind of even and odd.
Right. Okay. So like I mentioned, there are multiple applications of density functional theory. You can use this approach for condensed matter, a crystal, let's say, and calculate its electronic structure. You can calculate its vibrational and phononic characteristics. So if you're interested in the thermal behavior of a crystalline system, you can get into that. You can look at individual molecules and look at phenomena such as surface binding and calculate the various solutions or chemical binding energies for a molecule that is binding to a surface. Could be for catalysis applications, or so density functional theories can typically give you very accurate estimates of binding energies. You can look at free energies for chemical reactions, like Gibbs free energy. You can measure or calculate Gibbs free energy for interfacial processes or surface phenomena. And you can get into reaction rates and kinetics, which I'll present a little bit as an example very soon, which typically uses transition state theory to model reaction rates. You can model reaction rate constants through density functional theory. So with all of that, let's look at some examples. So we are at the hour. So do we want to take a break or continue?
Take a break.
5-minute break.
No, it's up to the students.
Okay. Do we continue or take a quick break? 2 minutes? Okay, sure. Let's keep it at 2 minutes then. No, not tomorrow. Still theory, yeah. Why do you ask?
Because I want to see your lab, and I'm determining if I should skip your lecture tomorrow.
Okay.
Talk to Juan David here.
Either way. Juan David.
Talk to David.
It's like they could be very
Okay. So we could do it after lunch tomorrow or something? Because I'm seeing over in the lab where some of these students are usually. So we can do it. Okay? Good. I'm looking at this reports my mom lives close to the place
Oh.
where there's the biggest fire in North America, etc.
So now did they elevate that level?
Um, she's still at the be ready level.
Okay.
So she's not at the level where they're making
Mhm.
her leave.
Wow, that's rough. But the air quality must be pretty bad.
Yeah, I'm sure. No, 0% contained. They have a website showing how much is contained.
The wildfire is in bad shape right now.
Contained, but that was
It's very dry where we are at. It's not so humid. It doesn't rain in the summer.
I told him we could send some
In
lunch.
Pullman, it doesn't rain much in July, August, September, June, July, August. It's pretty dry, and it gets pretty hot. So, you know, the grass and everything dries up. Right. Forest fire.
My mother lives on a ranch by herself. She's almost 90 years old. She has like about 500 acres that she lives on. So there's trees and big
Is
hills.
the fire near that?
Yeah, pretty close.
Really?
Yeah, so her land's not on fire yet. But
So, does she have anyone who checks on her periodically, or neighbors? Or? Well, if it's 500 acres, probably not a neighbor.
her and the other old ladies that are, you know, out in within 10 miles of her, they kind of all know each other and check on each other. And then the siblings, of course, are all checking, but they've closed the interstate, so my brother can't go down or anything. I was just looking at the fire, got a new update, so I was checking it. She's a honoring 90-year-old lady. Fires won't scare her at all.
Yeah, but if it is needed to move out from there, it will be difficult for her alone rather than somebody to help
Yeah,
her.
she said she put a bag in the car, so if she needs to go, she can jump in the car and drive away.
Okay. Some alternative plans.
Mhm.
She's very confident in herself.
She drives then, right?
Yeah,
She still drives.
very independent. Yeah.
Nice. I would love to be that way at that age.
Yeah, sometimes they have to be, you know,
It depends a little bit on your kind of, yeah, how strong you're mentally and also physically, I guess, right? If,
Well, it is good to be independent.
oh yeah, of course.
You don't need anybody's help. Always not somebody is helping you. And, you may not get somebody to help
Mhm.
you sometimes. So.
2 minutes over.
Yes. I think it's 5 minutes almost.
Right.
2 minutes is too short. I mean, going and coming back, it will take 2 minutes.
I didn't want you to think I was playing video games over here.
I was confident you were, but anyways, now I know.
Now I can play all I want.
Okay. Let's get started with an example. I'll let you guys settle down. Okay, the first example I have is related to one of the applications that I've discussed earlier, which is my work with lithium-air batteries. But that doesn't matter so much. This is a physical system that could be relevant to a lot of other problems. So you have a surface, in this case a lithium crystal, which kind of simulates the lithium-air battery anode structure. And the electrochemical reaction that happens during discharge is the lithium atom from the crystalline structure kind of oxidizes, and it loses an electron and it gets solvated in the electrolyte that is surrounding that crystalline structure. In this case, it's an ionic liquid, which is a pretty complex electrolyte, like I had mentioned. It's a liquid salt comprising these cation-anion pairs. What we are interested in knowing is the energy associated with the solvation process, as well as the rate at which it happens. Calculating the energy is probably not super complex, but determining the rate for these reactions at discharge is not straightforward. It had not been done when we started working on this. So the question was, how do we estimate the rate, get into the kinetics for this, right? And what does it give us, basically? What can we determine from this? Why is it important? The reason it's important is if you know the rate constants for these reactions, let's say Ka, which is this process at the anode, and a corresponding rate constant at the cathode, you can use this continuum mechanics formulation or model called the Butler-Folmer equation to estimate the current density for the battery, which is a very important parameter. So therefore, it's very important to calculate these rate constants Ka and Kc. We will look at Ka in this work, which is for this reaction where lithium from a solid crystalline state gets to ionizes and gets solvated in the electrolyte. Once that happens, then the lithium ion has to obviously diffuse through the electrolyte to the cathode, but we are not addressing that in this particular work. So it's a function of the electrolyte that you have in the battery. So in this case, like I mentioned, the electrolyte we are considering is an ionic liquid. Its chemical structure is shown here. This is a 1-propyl-3-methyl imidazolium based cation. This is a positively charged ion in the electrolyte, and it has an anion that I will show you in a later slide. So what we were interested in this particular project, what happens if we change the cation structure? How does that?
This is in battery.
It's a battery application. So we have this liquid electrolyte, and we were interested in knowing how the electrolyte cation structure impacts the rate for this reaction, which is this the lithium ion getting ionizing and solvating in the electrolyte. So how do we determine that? The theory that we looked at for this particular process is called Marcus theory. Marcus theory is not really very frequently applied to electrochemistry, but it is very popular. Marcus won the Nobel Prize for developing this theory. It's very widely applied in biochemistry, where there is a lot of times you look at electron transfer reactions in proteins and as such, those kind of systems. So we took the Marcus theory and tried to apply it to solve this problem, to determine the rate constant for these electron transfer reactions. So the Marcus theory's model is shown here on this slide. So you have an energy term, right, an Arrhenius type term, and a prefactor. Okay. So what are the key parameters in this? There is the total Gibbs free energy that drives that electron transfer reaction. So the Gibbs free energy is obviously very important for any chemical reaction. And then there is this term lambda. It's called the reorganization energy. I'll explain reorganization energy in a moment. So essentially what the Marcus theory does is you have a donor and an acceptor that are both in a solvated state, and the donor donates an electron in that solvated state to an acceptor. So donor becomes ionized as D plus and the acceptor becomes A minus in a solvated environment. So the rate for this reaction is captured through these parameters, the Gibbs free energy, the reorganization energy, and what is called a coupling matrix or coupling parameter for this process. So let's look at this in a little bit more detail. So this is a very popular way of explaining Marcus theory. You have, let's say, a donor. In a chemical reaction, you have a reactant and a final product. In this case, you have the lithium atom in a crystalline state, and this is the energy landscape for it. It shows the energy for that structure. And you have the lithium plus cation in the solvated state with a certain structure. So what we need to parameterize or calculate here is the Gibbs free energy and the reorganization energy for this electron exchange process to happen. And the Gibbs free energy is defined by the difference in energy for the lowest energy state for the lithium and lithium plus in the solvated state. And the reorganization energy is also shown here in this diagram in this fashion. Okay. So the Gibbs free energy, which is very important in density functional theory, this is often done in this way. When you have a physical process or a chemical reaction, the total Gibbs free energy for it is broken down into sub processes. Sometimes these can be hypothetical process, but you come up with a free energy cycle. So, you have a reaction, you break it down in pieces, find the energy change for each of these and add them up to get the total energy for that process. So, in this case we can think of this electron transfer reaction in these 3 steps. The first step is we take a lithium atom in the crystalline state and think of it to vaporize. So, we can find the vaporization free energy for the vaporization process, where you are taking it from a crystalline state to a vapor state. The next step is for that in the gaseous phase for that lithium ion or atom to ionize. So, lithium in a gaseous state goes to a lithium plus ion and loses an electron. And the third step is for that lithium plus ion in the gaseous state to get solvated in this specific ionic liquid in the so the reaction corresponding to that. So, our goal was to calculate the delta G for this vaporization process, the delta G for the ionization process and the delta G for the solvation process. If you add these 3 up, you get the total delta G for this reaction to occur. Okay. I talked about the reorganization energy. So, what is the reorganization energy? And this is very specific to Marcus theory. There are 2 types of reorganization energy, and the total reorganization energy is a sum of these 2 terms. The first one is called the inner sphere reorganization energy, which describes the change in structure, electronic structure of these reacting species as the reaction happens. And then there is outer sphere reorganization energy, which relates to the solvent relaxation process. So, the electron exchange is happening in a solvated phase, and as this process happens, the solvent molecules around the lithium ion will relax, that is, go from a higher energy state to a lower energy state, and the energy associated with that relaxation process is called the outer sphere reorganization energy. So, density functional theory was applied in this case to calculate the Gibbs free energy for these individual reactions and the inner and outer sphere reorganization energy. Once you have that, you can use Marcus theory to calculate the reaction rate. So, in this particular, so just a brief introduction, density functional theory, there are many software out there. One of the most popular for material scientists is called VASP. Okay, it is a Vienna ab initio software package. I am sure some of you are nodding. It is a very popular package used for condensed matter crystalline system. On the other hand, a lot of chemical engineers interested in chemical reactions and catalysis apply a package called software called Gaussian. Again, it is very popular. And then in this project, we use all different software depending on our particular application. In this case, we applied a package called NWChem. This is actually developed in a national lab, which is pretty close to where we are at WSU. It is called PNNL. It is their in-house software. We applied the NWChem software. When you apply DFT, you have to consider a level of theory and basis set to perform that DFT calculation. In this case, we used a very popular B3LIP exchange correlation functional, which describes the electron density, and we used periodic boundary condition for the the crystalline system, and for that we used PBE GGA functional and a certain basis set. So, when you run a DFT calculation, you have to worry about the basis set and the functional, which is called the level of theory. Okay. So, that is what we did for this. Now, you might be wondering, the ionic liquid chemistry looks pretty complicated. It is not very straightforward, their structure, right. This is again the imidazolium based cation, and this anion is called TFSI. So, this is not a very straightforward structure. So, how do we calculate the solvation free energy of a lithium ion that is surrounded by these complex molecules or ions in this case? A very popular approach in density functional theory is what is called implicit solvent model, where you are actually not modeling at an atomistic sense the solvent molecules, but what you are doing is you are modeling the solvent in an implicit manner. There are many models. So, for example, if you are using the Gaussian software, there is the polarizable continuum model which treats solvent molecules implicitly. In NWChem, what is implemented is the so-called Cosmo model. It is called the conductor like screening model, and the reference is here. The parameters that go into the conductor like screening model or the Cosmo model are the dielectric constant for the solvent, which is a very important parameter, what is called the solvent accessible surface, and then the atomic radii of the solvated species, in this case the lithium ion. Okay? So, these are input parameters to the solvation model. So, how do we get, in this case we chose a bunch of cations for which we had these parameters available from experiments, and those cations, like I mentioned, in this case were the 1-propyl 3-methyl imidazolium cation. What we did is we varied the side chain length to look at the impact of the structure on the reaction rate constant for the electron transport. So, what we did is we considered a variable chain length going from a chain length of size 2, that is ethyl chain, ethyl functional group here, to propyl, butyl, and so on and so forth, all the way to an 8-member chain. So, we varied the side chain length. The key parameter for that is the solvent radius with variable, meaning this cation radius for variable chain length, and obviously the bigger the chain length is, that radius goes up, as you can see from this red curve. And we also obtained from experimental measurements the static dielectric constant for these ionic liquids with variable chain lengths. So, those are shown here. Essentially, the key idea is the dielectric constant goes down, reduces as you go up in the chain length for this cation. The anion in this model system was this TFSI. We didn't change the anion structure for this study. Okay. So, again, this is the system description. At first, we, like any model, we validated our calculations by comparing with experimental measurements. So, this shows you some calculations for the first ionization energy, the vaporization energy, and cohesive energy, and the agreement with experimental value is pretty decent. So, with that we moved forward with our calculation. One of the very important parameters here is the solvation energy for the lithium ion. So, that plays a huge role. So, solvation energy is the difference in energy between the lithium ion in the solvated phase and the gas phase. Remember, we broke it down in these 3 steps. So, this is the delta G this is the delta G solvation, which is the difference in energy between the lithium ion in the gas phase and the solvated phase.
But why it not go to liquid, so solid to going to measure, why does it in liquid in between solid and gas?
So, what we do is, this is called the thermodynamic cycle approach. What we do is break down the reaction which goes from lithium in a crystalline state to a ionized solvated state, break it down into 3 independent reactions. The first is taking that lithium ion out of the crystal, so kind of vaporizing it. Okay. And then from there you ionize it, and then you convert it to a solvated phase, and you calculate the energies for each of these pieces. I am not presenting the energies for the first 2 steps because it's very straightforward. But what is very critical here is the solvation energy, because guess what, we are trying to find the rate constant for different solvents, right, different ionic liquid electrolytes. So, the first 2 steps do not depend on the solvent. The energy associated with taking a lithium atom out of the crystal into the vapor phase is not solvent dependent, but this reaction, the solvation process, depends on what solvent or electrolyte you are using. So, what you see here is the gas phase energy of the lithium ion, which is nearly constant, and the energy of the lithium ion in various electrolytes that we considered. Remember, the electrolytes are with a side chain length of 2, 3, 4, and all the way up to 8. So, what we find is the energy goes up with the chain length. So, basically, as the chain length goes up, the dielectric constant of that ionic liquid decreases, right. So, with increase of chain length, the dielectric constant decreases, which leads to the pattern that we see or trend we see in the solvation of the lithium ion, the solvation energy. So, if we find the difference between these 2, we get the magnitude of the solvation energy, free energy for the lithium ion as a difference of these 2 energies, and it follows a almost linear trend, which was initially very kind of surprising for us that we found this kind of linear trend. So, we went back to the literature and found this paper from Tijong and Zhao, which comes up with this model for solvation free energy as a function of the dielectric constants, and this kind of predicts this sort of linear behavior. So, this behavior was consistent with the model from Tijong and Zhao. So now, from all the different components of energies that we calculate from our DFT, the vaporization energy, the ionization energy, and the solvation energy, we add all of them up to get the total free energy for this reaction to happen, which is represented by this pink line here. So this shows you the free energy for this reaction to proceed. Now, what do we find here? The magnitude of the free energy drops as we go from the left to the right. And what is the x-axis here? It's 1 over the dielectric constant. So if 1 over dielectric constant is basically reducing in the along the x-axis, what we have is dielectric constant is increasing, and we know that as the dielectric constant increases, the chain length decreases. Okay, so that's the trend that we capture here, that the total Gibbs free energy, the driving force for this, decreases with the increase in chain length of the ionic liquid cation, and therefore impacts the total contribution to the total free energy for this reaction. We also calculated the inner sphere and outer sphere reorganization energy. So again, this inner sphere reorganization energy has to do with the electronic structure of the reactant and the product as this electron exchange process is happening. Technically speaking, the method that is applied for finding the inner sphere or reorganization energy is called the Nelson's 4-point model. I am not going to discuss that in detail here, but the model for outer sphere reorganization energy is shown here. So this is, there is a mathematical model that is used for looking at solvent reaction. Not surprisingly, the key parameters for solvent reaction are related to the optical and static dielectric constant of the solvent, which is basically the ionic liquid electrolyte. So that is all accounted for, and what you see in this plot is the inner sphere and the outer sphere reorganization energy as a function of 1 over dielectric constant. Okay, so this is a high dielectric constant, this is low dielectric constant. So we have calculated all these components in the Marcus theory. The next step is to combine them to find and calculate the coupling matrix to calculate the electron transfer rate constant from this expression of Marcus theory, which is what we do. So this plot shows you the logarithmic plot of the rate constant with the chain length of the cation of the ionic liquid. So you see the trend is as we increase the chain length, the rate constant drops, and that's because we correlate this to the dielectric constant or the dielectric behavior of the solvent, because with increasing chain length, the dielectric constant, static dielectric constant of these ionic liquids go down for higher chain length, which is related to the reduction in the rate constant for electron transfer with these ionic liquids. So, questions?
What is inner and outer solvation means?
Inner and outer reorganization energy? Okay.
Yes.
So, the inner sphere reorganization energy, if you go back to the plot for Marcus theory here, is the contribution due to the change in the electronic structure as this reaction happens, the electron transfer reaction happens. The electronic structure of the lithium ion and it changes. So, that is the inner sphere for the reactant and the product. The outer sphere reorganization energy is the contribution from the solvent relaxation. So, as this process happens, the solvent molecules rearrange and reconfigure, right. So, that is called solvent relaxation, and the contribution, energetic contribution from that solvent reorganization process is called the outer sphere reorganization energy. So, we are basically trying to model this jump of electron from the crystalline state to the ultimately the solvated state in the electrolyte, and our goal is to understand the rate for this process, which depends principally on the total Gibbs free energy that drives this reaction, that is the driving force, and the reorganization energy. And what we find is the key parameter, if there is one parameter that is the most important here, is the dielectric constant of the solvent, and therefore the dielectric constant, as I showed you from experimental measurements for these ionic liquids. Okay, give me a moment. Yeah, so the dielectric constant, the static dielectric constant drops as we increase the side chain length, which leads to reduced Gibbs free energy that drives this reaction, because solvation is the key process there. Also, it leads to a reduced reorganization energy. So, the driving force for the reaction, kind of based on the energetic measurements or contributions, drop as the size of the anion, the cation increases, and that leads to a slower electron transfer reaction, which will have an impact on ultimately the exchange current density of the battery electrolyte. This model is pretty powerful because what you can do, you can see this fit, right. So, because we used an implicit solvent model, the Cosmo model here, essentially if we find another solvent which has a dielectric constant somewhere here, we could kind of use this curve fit to predict the electron transfer rate for that as well. Is these data points, even though they are for physically this ionic liquid cation, we are using an implicit solvent.
So these are organic solvent.
These are organic solvents.
So we can find also inorganic solvent, or
you can use this model for the organic solvent, but the dielectric constant for organic solvents is going to be way out of this range that we are looking at. So you can't use this to predict the same electron transfer rate constant, for example, with DMSO or dinitrile electrolytes, or any common carbonate, organic carbonate electrolytes.
how to choose the solvent, means how do you decide that this is a solvent?
So that's the big deal, right? That was the goal of this project, to see what are the parameters of the solvent that, if you wanted to choose an ideal solvent for electrolyte, then this is not the only consideration. This is one of the key considerations, but there are others like the ionic conductivity, the vapor pressure, the viscosity. So it's a multi-property space that and consideration that goes in for choosing the solvent. I'm just presenting a piece of that consideration, one of the aspects. Yeah.
Sir, all these calculations are done at 0 Kelvin.
Yes.
Pressure is also 0 Kelvin.
Right. So these are standard 0 Kelvin DFT calculations. We didn't consider the actual dynamics of this process. Yeah. But the reorganization energy captured from this model should in a sense capture that.
So, since this involves a complex of LI plus and the solvent, so in this case also for the cone SAM model to be applicable, the relaxation has to be done, like we generate
Right.
crystal structure.
So if you are considering pressure equals to 0, then it should be Helmholtz free energy, no? Case of
Right.
Oh,
This is not, we are not thinking of it from that ensemble perspective. This is just minimizing the energy. Yeah, free energy. We did, but that's a good question. We did look at the temperature term, the T delta S. I mean, I can refer you to that paper. We did some calculations for the entropic, like kind of model that, looked at from that perspective, the entropic contribution, what that would be. There is a thermodynamic analysis that was performed. Yeah.
So in continuation to that question, so in this case it is lithium. So it is the S orbital coming into picture, which is a localized, like homogeneous localized. But in case of F orbitals,
Okay.
where the lobes are towards
Right.
concentrated at a different site. So in that case, this convergence is not.
Yeah, you have to use a different basis set that is appropriate, different model for F electron systems specifically. That will be different from this. So in those specifications are specific to the atoms that you are modeling. So yeah.
Can you suggest some, like, for a better convergence for the relaxation of the structure or F electron?
Sure. I mean, I have recently done some work with F electron systems. Let me share those with you afterwards. I can show you the model that we are applying for those systems.
Basically, sir, I work on the rare earth system, the neodymium
Okay.
system. So neodymium dysprosium.
Right.
So I'm looking for that because the convergence is creating a huge.
Yeah. Those are many more electron systems than this simple lithium, for sure. But those calculations that we are doing are ab initio molecular dynamics, so there is a DFT component to it. Let's discuss. I can share with you the methodology for those calculations for F electron systems.
So we are performing DFT, so we equilibrate our structure like we are doing in MD.
Sure. I mean, even with DFT, if you start with a energetically more favorable structure, your convergence is faster. In the convergence, you have a force minimization and energy minimization. So if you start with a closer to real structure, then yeah, that minimization happens. Any software you use, even if you are just using software to develop that structure, let's say Avogadro for a molecule, those have some energy minimization software solvers that you can first apply to kind of relax the structure and then use that. So you can do this in steps. Right. Okay. So let's look at another application for this, which is entirely different from the one that I discussed so far. It is the density of states or band structure of a perovskite surface. Okay. Again, a different application, and I talked to you a little bit yesterday about processing of electron transport layers on top of these perovskite. Remember, the motivation there was related to mitigating defect states that are present on surfaces of perovskites. So what we are trying to address here was what is the impact of atomistic defects in these lead halide hybrid perovskites on their electronic structure, looking at their band gaps, and if there are any deep level trap states or shallow trap states that are generated when you introduce defects, such as, there are many defects that are seen in the perovskite structures here, including interstitials, vacancies, antisites with different formation energies. So obviously you want to consider defects with favorable formation energy, that they are relevant, right? So for bulk perovskites, it is already known that the defects that are most relevant do not introduce deep trap states, but what is not known at the time we started this was what about surface defects? I mean, if there are defects present at the surface of a perovskite layer or film, how does that impact the band structure? If it does introduce a shallow defect state, then probably we are okay. If it introduces a deep level defect, then how do we mitigate that? Perhaps by changing the processing conditions, which is what we will find out, or by addressing it by introducing an electron transport layer to mitigate the defect. So the defect that we considered for this calculation, energetically favorable defect, is called the lead iodine antisite defect. Okay, so where you are substituting a lead atom on that perovskite film with an iodine and trying to see what that does to the band structure. Again, this is the detail. In this case, we use the software VASP, and we use a generalized gradient approximation with PBE functional for exchange correlation. I believe we also accounted, we did account for van der Waals interaction, because this is an inorganic organic lead halide. So that is kind of important. So we used a functional for the van der Waals, and we kind of did sensitivity study for the parameters that we use, such as cutoff energy and force convergence criteria. One of the key things when you are looking at a slab, if you're not looking at a 3D periodic system, is to make sure that a couple of things. Number one, there is no effect of confinement. So you want to have a slab that is thick enough that there are no effect of confinement or quantum effects thereof. And if you have a supercell, making sure that in that z direction, there is a planar direction where it's periodic. In the z direction, the distance is significant. The other aspect that we did a sensitivity analysis on is if you introduce an atomistic defect, your xy direction, the planar dimension of the film, has to be large enough that you don't have any defect interactions, spurious defect interactions, because what we really wanted to model is dilute defect concentrations. Okay, so we did some sensitivity study to choose the appropriate system size, which is always very important. So first, what we did is we looked at what happens if you have antisite defect, the lead iodine antisite defect, in bulk perovskite crystal. So we are not talking about, this is just a periodic cell, bulk crystal. So this is first of all the band structure for bulk perovskite, and our calculated band gap was, I believe, 1.57, about 1.57 electron volt, which compares pretty well with the measured band gap of these perovskite, which is about 1.6 electron volt. So what we found is, if we introduce a defect, this lead iodine antiside defect to the bulk structure, it leads, if you compare these, it leads to a couple of shallow level defects, but because they are shallow defect, that shouldn't really impact the the photovoltaic performance of these films. So next we went to what we were actually interested in, which is the surface. So there are two types of terminating surfaces in these perovskite. One can be where the surface is terminating with methyl ammonium iodide groups, and the other is if the surface is terminating with lead iodide groups. Okay? Yeah.
So how you are differentiating between shallow and deep defect?
So where they are located. So a deep defect state will be somewhere at the mid of the band gap, right? Band gap region. While the shallow defect is pretty close to the edge of either the conduction band or the valence band. Either it is close to the valence band maxima or the conduction band minima, so that non-radiative recombination effects for the electron that is hopping will not be as pronounced as if it's a deep level defect state somewhere here. Then you would lose that electron, right? It will recombine, and that is a very important consideration in photovoltaics.
So in that diagram, sir, it is density of state in the positive direction, so
Mhm.
only the upstream electrons
Right.
have been considered
Mhm.
in this diagram.
Right.
Sir, is there any specific reason why the downstream electrons were not considered?
This is if you are interested in just looking at the band gap and the defect, the upspin electrons are typically what you care
Or
about.
it is basically only for the band gap.
Right, exactly. So now we are looking at the methyl ammonium iodide terminated surface and introducing the same lead iodine antiside defect, and what you can see is there is a pronounced defect state here, trap state that is produced, but it's still a shallow trap state in the sense it's not close to it's not at the mid level of the band gap region. So what we were interested in finding is correlating it, number one, with the structure of this perovskite surface with the defect, and trying to find what are the contributors to these defect states or levels, right? So we did a partial density of state calculation for the different atoms in the system: carbon, hydrogen, iodine, nitrogen, and lead, because it's a methyl ammonium lead iodide. So these are the constituent atoms. And what we found is the primary contribution to this is the iodine atoms of this system. So iodine is the primary contributor. So next we wanted to figure out what happens here. I mean, which iodine atoms, are there specific iodine atoms that contribute to the defect state? It is known from experiments that iodine atoms, if you synthesize these structures in an iodine rich environment, a lot of times it introduces clusters of iodine, or the antiside defect, there is an iodine side that kind of forms weak covalent bands. That has been shown for other surfaces or other defects. So we wanted to see if we see the same effect for this particular perovskite surface. So this partial density of state basically looks at what we found from the structure here is this is the defect atom, the iodine I1 at the antisite, and then within 4 angstrom it is coordinated with 6 other iodine atoms, which are classified as I2, 3, 4, 5, 6, 7. Okay, 4 of these are in plane. So 4, 7, 5, and 6 are in plane with the atom I1, and then 2 and 3, I2 and I3 are out of the plane. Okay, interplanar defects, iodine sites. So when we look at the partial density of states, we can see the impact of these in plane and out of plane triad, and one of these is a 5-fold coordination. So it is a group of 5 atoms, and the out plane is 3, and we can see the impact or the contribution to this trap state from all of these 7 iodine atoms. So, iodine, the defect atom I1 has the largest contribution, but then I6, I7 and the contribution of I5, I6, I7 and I4 is also shown here along with the in the charge density. Okay. And to really understand the nature of binding of these atoms, we did a beta charge analysis, which is pretty typical here, to find how does the introduction of this defect iodine atom change the charges, the partial charges on these iodine atoms. So, we compare the situation for a defect free structure, these are the partial charges, with the charge in presence of the defect. So, obviously, the defect atom has a small positive charge, and you see that the other atoms, you can group them into the I2 and I3, which are the out of plane, have a somewhat reduced charge. So, there is a significant reduced charge, actually reduced by up to 50 and 30%. On the other hand, the in plane iodine atoms have a somewhat lower charge, and their charges are kind of similar. So, we conclude here that there is electron sharing between the defect atom and this cluster of 4, which contributes to this trap state that is generated. The other 2 atoms do not contribute anything to the trap state for the methylammonium iodine surface. But even though this the methylammonium iodide terminating surface with defect introduces this trap state, it is a shallow trap state. So, we would not be concerned as far as the performance of the device goes for this situation. But we are interested in looking at the other situation, other structure, which is the lead iodide terminated surface of the perovskite, and to determine what happens if you introduce the same lead iodine anti-side defect to this terminating surface. So, here is a comparison of the lead iodide, the surface with lead iodide terminating group without defect and with defect. It is immediately clear that there is kind of a deep level trap state that is generated as you introduce the anti-side defect here. And again, we are interested in running the analysis to check what contributes to this deep state defect. There is also a shallow state defect that I did not mention, so at the edge of the conduction band, but we are also interested in knowing what contributes to that state. So, here is a structure of the lead iodide terminated surface with the anti-side defect. In this case, again we are calling I1 the anti-side location for that defect, and it is surrounded by a group of. So, if you do a nearest neighbor analysis, the major cluster is formed between these with these other 4 atoms, which is I2, 3, 5 and I2, 3, 4 and 5. I6 is a little farther out. So, they are kind of in plane, this group of 5 atoms, and we were interested in finding the contribution of these atoms to both the shallow level defect state and the deep level defect states, which are shown in these plots. So, this is the deep trap state and this is the shallow trap state. Okay. Yeah.
So, if I'm right, these are the thin slabs you have designed.
Right. Right.
So, in the earlier you said that the defects which you are introducing, you are trying to introduce the defects such that they are not interacting with each other.
Right.
So, now in this case, we can see that you are showing some schematic where you are showing indium with the nearest indium.
Iodine, you mean?
Sorry.
No, so those other iodine atoms were already in the structure. Yeah, so we only introduced one site for the defect, which is the atom I1 at a site which had lead. So, instead of lead, we swap it with iodine, but the other atoms were already present in that structure. So, that is the only stoichiometry that we changed. But going back to the question we had earlier, this required quite a bit of energy minimization first before obviously we do the density of states calculation. It's pretty intensive, the energy minimization, and at first we used a slab size where we did see some spurious effect of defect interaction, but then as we kind of introduce more atoms, increase the XY dimension of that slab. Let me see, I don't remember off the top of my head. Let me go back to the paper. So your question is, what is the size of the system here, right? Give me a moment. Okay, is it sharing this, my screen? No? Okay. Okay, so for bulk calculation we used, oh, you have to plug it out. I can read off the paper, I mean, it's not completely necessary. So it's a, for the bulk calculations, we used a 2 by 2 by 2 tetragonal perovskite structure with 384 atoms. So, and the MAI and lead iodide terminated surface were 1104 and 1008 atoms. So these are pretty big systems, DFT level. I mean, we ran these at cluster at Idaho National Lab, and it took quite a while to converge. We are talking about weeks. So, yeah, these are pretty intensive calculations. Okay. So, analysis of these clusters shows us that basically the contribution to the shallow level defects are from I4, I5 and I1, while the deep level defects were from I2 and I3. So, basically we were able to connect the structure, and the basic origin of this impact of the creation of this deep level defect state is the covalence of the iodine-iodine bond that is created in this cluster. And we were able to detect it by looking not only at the charge analysis, which shows electron sharing, but also the kind of distance, which is, I think the covalent bond length in iodine is about 2.7 angstroms. So this is not really a covalent bond, it's a weak bond, but some of these are pretty close, like 2.86 angstrom. So this covalent interaction or electron sharing leads to the two defect states. Now, how would you? So this is kind of the summary of what we found. That the clusters of iodine atoms and the specific nature and size of the cluster determine the terminating group determine the type of defects that are created in these perovskite structures. In methyl ammonium surfaces, 110 surface, it's a 5 in plane and 2 out of plane cluster, while for the lead iodide terminated surface, it's 5 iodine atoms that are on the top surface of the perovskite. So this is a pentamer. Now, do you have to be, so in practical applications, the anti-site formation energies are relatively large under iodine poor conditions. So if you are kind of trying to get around this, then this says that you would have to use precursors that are kind of not so rich in iodine, so that you don't have these clusters forming, and that would reduce the chances of those trap states that ultimately would lead to loss of performance in the perovskite photovoltaic solar cell. So I think that's all I have. I have another example, but I don't think we'll make it. It's going to take quite a bit. Questions? I wanted to kind of present an example of an ab initio molecular dynamics calculation that we have done. I guess tomorrow I can use up the first half an hour of the lecture to present that before we get into Monte Carlo. So we'll keep it there.
An example of DFT simulation.
These are DFT. These are 0 Kelvin, no dynamics. These are just.
no molecular no more intermolecular interaction.
You can add van der Waals terms, correction terms, to address that for a specific system. For the perovskite, we did include van der Waals dispersion terms.
Okay.
Again, it increases the computational cost.
Hmm.
So typically when you are running these DFT simulations, as those you are doing it are familiar, you use a few different levels of theory and basis sets to kind of compare your structure with experimental measurements like lattice parameters if you're looking at condensed matter systems. And that way you kind of know what is the appropriate level of theory and basis set for that particular system.
Sir, in case of sometimes like iron and supposedly the titanium nickel is there. Suppose they pair ferromagnetically or
Mhm.
ferromagnetically. So if we want to find out if any two elements in the D block, so can there be any generalized way in DFT for doing this? Just we want to find if they pair ferromagnetically or antiferromagnetically.
You would have to run like sensitivity study, and there are few different effects that I didn't mention here that are pretty important for these systems. One is the spin orbit coupling, relativistic effects. So, you know, basically when you're looking at those specific systems, you have to read up the literature and what's the standard, and then compare different, like I said, levels of theory and basis set to see if you're getting some validation.
Calculate a J parameter you are
Mhm.
telling, sir, the sign of J parameter
Right.
will determine.
Mhm.
So in that case, sir, we proceed with the normal density of state
Mhm.
calculation, or is there any other method to do that?
That's all I'm aware of. Yeah, the normal density of states calculation.
Okay, so by the density of states, we
Mhm.
like the upstream and downstream, then we calculate that J parameter.
Right.
Sir, can you briefly talk about spin orbit coupling? Actually, we usually realistic
Relativistic
yes,
pseudopotentials.
Can you talk a bit on this?
So what sort of systems are you?
So actually, Bismuth telluride system, PA2, PA3, which is a layered
Yeah.
structure actually, and in between there are bundle of forces also, and if we consider this SOC, then
Mhm.
how, what do you say about it?
The spin orbit coupling seems to be very important for those systems for sure, so you have to account for them. So what theory are you using? I mean,
Actually, I want to know the electronic behavior
Mhm.
on dispersion.
Mhm.
So the actually this system is known material for thermoelectric.
Oh, okay.
So for that we need to understand the electronic transport behavior.
Mhm.
That is phonon transport and feedback from this going.
So you're using VASP,
Actually I'm just trying to use the quantum espresso.
quantum espresso. I'm not sure if I mean, VASP has very good,
Yeah,
you
but
know,
it's commercial. So
it is commercial, but you know, it has some good theory for looking at those thermoelectric materials. I know that, you know.
we can combine the DFT with the bootstrap, and then we can find out the temperature dependence of these properties also.
Are you also looking at the Boltzmann transport theorem for this phonon?
Yes, mixing the bootstrap, there is one code called bootstrap.
Okay,
So
I am not aware of that.
That uses the Boltzmann equation
Okay.
for calculation. But the initial inputs they require from the DFT.
Oh, I see. So, you know, are you looking at two phonon cyst calculations, or, you know?
So right now I haven't focused more on the phonon, but I am just focusing right now on the
So you are basically getting the right structure from the DFT
structure
first.
and the electronic behavior.
Okay. Yeah.
But I am just using the very basic pseudopotentials without considering the SOC. So
As far as I understand, for those, you do have to look at spin orbit coupling for bismuth telluride. Okay. Well, there are no more questions. Thank you for your attention. So let's discuss your systems a little bit.
Right, sir. I want to make
Let me
it,
get, yeah, let's, I think it'll be nice to meet.